So I just want to make a small introduction because there are people in the room which are not from the field. Why we do this workshop? It's because it's a 150th anniversary of the BIPM, as our director reminds us. It was a busy year for the BIPM to organize that. It's also this Saturday, it will be the 150 years anniversary of the discovery of the ionizing radiation by Röntgen in 1895. And it's also the 65 years anniversary of the decision by the CIPM to create a new section of the BIPM, which will become the ionizing radiation department. And the second part will be to get a vision for the future of ionizing radiation metrology. But first, what are ionizing radiation? Just to put the framework, so we are speaking about radiation with enough energy to ionize atom, so it means with energy higher than 10 electron volts, so it means charged particles, photons, which are X or gamma rays, and neutrons. And we do not consider every low energy photon ranging from radio wave up to ultraviolet light. Ionizing radiations today are supporting worldwide needs, so we have about the health, you have diagnostic imaging, you have the radiotherapy. For the industry, you have also sterilization of medical devices, you have irradiation of foods, you have the protection security for radiation protection, also the nuclear forensics, which are something about homeland security related. You have the nuclear power, of course. Nuclear power, it's 10% of the world electricity. There are a lot of development, a lot of work on new small modular reactors, which will be part of the grid electricity distribution, and all the problem of what we do with the waste we have created since decades with this source of electricity. And environment and climate are related because of that, but also because of the natural radiation monitoring, the radioactivity in air, soil, and food. And if people want to restart some experiments with nuclear things in the air, it will be very important. And nuclear isotope techniques used to monitor the greenhouse gas emission for the climate change will be also a tool that can be used. So this is the landscape. And what is ionizing radiation metrology today? So there are first a dosimetry. So the dosimetry is how we assess the amount of energy deposited by ionizing radiation, except the neutrons, in a given medium that we call the dose. That's very straightforward definition. All the experts will say yes, but okay, that's my explanation, simple explanation. So what is required is a few well-defined radiation sources and the standards to measure the dose. The radionuclide metrology is to determine at the end the radioactivity, but for a correct determination of the radioactivity of all these unstable isotopes that emit radiations, which we call radionuclide, you need to determine the half-life, the emission energy, the decay mode, and what you require is a accurate amount of radionuclides that you can measure precisely. You have a 4-pi or equivalent system to measure all the emitted radiations of every nature. And third part is a neutron metrology. So it's a distinct field because the neutron being indirect ionizing particle, it has much more complexity to be determined. So that's why the accuracy of neutron metrology is not so good as the others. But you determine the number or rate of neutrons per unit of area, which we call fluence, or emitted 4-pi by radionuclide neutron source that we call emission rate. And the dose determination can only be determined if you know all the energy distribution of your neutrons, which is a wide range of energy. So what you need is a few well-defined radiation sources, standards to measure the fluence or the emission rate, and neutron spectrometers. And how it's organized, so you have, at each country, you have either national metrology institutes which are in charge of ionizing radiation metrology, but in most countries, because it needs specific activities and knowledge, it's designated institutes which are in charge of ionizing radiation metrology. Both of them, they are members of regional metrology organizations that we call RMOs, and where we meet these people is within their technical committees of ionizing radiations, or in the Comité Consultative d'Environnement, the CCRI, which is mostly what will happen this week. So there are 3 fields. Those 3 fields are dosimetry, section 1, radionuclide metrology is section 2, and neutron metrology is section 3. The aim of all of this is to organize comparisons of the national standard, so we call CCRI or RMO comparisons. The CCRI, the Ionizing Radiation Consultative Committee, is referring to the CIPM, which is the Comité International des Poids et Mesures, which is a body of 18 members, which is elected by the Conférence Générale des Poids et Mesures, which is a decision-making body which manage or gives a big the big directions of this BIPM landscape. And all these bodies are there to provide a direction for the BIPM headquarters, which is Bureau International des Poids et Mesures, with 70 people in it. And among the 70 people, you have a department, which is Ionizing Radiation department. And there are others about time, mass, electricity, gas, and organic chemistry. But we only have activities in dosimetry and radionuclide metrology. Neutron metrology was at the beginning, but was stopped, and maybe we will have some history about that by Penelope in a few moments. So the NMIs and DIs can also use the BIPM as a way to make comparisons or to also perform calibrations of dosimetry secondary standard. But there is another body, which is IAEA, and they have built with WHO and IAEA coordination, a SSDL network for dosimetry, and they are traceable to BIPM, which allow also these NMIs and DIs to make bilateral IAEA SDL comparison on mostly to perform also calibration of dosimetry secondary standards. So that's the whole picture. But if you want to do all these things, you need also to have quantities and units. And so this is the ICRU, that is mostly what we do. And we will have François, which will explain us how all these things have been done. There are standards, ISO or ESA, no presentation today about standard, but they are there. And this is also for radionuclide metrology. There's also an international committee of radionuclide metrology, which is building all the scientific background. So coming back to the history, 160 years ago, 8 November 1885, discovery by Wilhelm Röntgen of the X-rays. So he just sees that there is invisible rays passing through solid materials and producing images on photographic plates. As he doesn't know what it is, he just says, okay, let's call it X-rays. And this is still what we have today. Then 1 year later, Henri Becquerel discovers the natural radioactivity. So, and Röntgen and Becquerel are, Röntgen is the whole unit, Becquerel is still an active unit. Discovery of the electron by Joseph Thomson 1 year later. Discovery of polonium and radium that confirms that some elements continuously emit radiation, so confirming the first observation by Becquerel. Curie was also a unit, especially in France, and a classification of radiation by Ernest Rutherford was done in the years later. So it's him who defined, okay, let's call alpha rays, beta rays, and gamma rays. And this is where the story will end, when I will give the floor for the start of the history of metrology. But just to remind that it is only a few decades later that Chadwick discovered the neutrons. So, okay, so that's all I want to say. Thank you very much.
Good morning. I would like to start first by thanking the organizer. It's my pleasure to start this historic session in providing some insights on the history of the first international radium standard and highlighting how the BIPM was charged to keep it. On 21st February 1913, Marie Curie and André de Bierne, her closest collaborator, traveled across Paris and crossed the bridge to deposit on behalf of the International Radium Commission the precious standard Marie Curie had prepared with the support of André de Bierne at the Curie laboratory. Marie Curie passed through the gate of the BIPM and walked past the great chestnut tree that you can still see at the entrance of the BIPM site. 10 years earlier, she had posed with Pierre Curie and their daughter Irène. One of the Sundays she spent with Pierre and Irène Curie at the BIPM. In 1910, she had published the Treaty of Radioactivity, and in collaboration with André de Bierne, she isolated metallic radium. From 12 to 15 September 1910, the Radiology Congress met in Brussels in conjunction with a universal exhibition which had been taking place since the 23rd of April. And at this Congress, where most of the eminent scientists in the field of radioactivity met, the need to produce reference standards to be used for comparisons in different laboratories was discussed for the first time. An International Radium Standard Commission was set up, composed of 10 members, with Ernest Rutherford as president and Stephen Meyer as secretary. And the first task of the commission was to prepare a radium standard. Marie Curie, who had acquired, of course, a significant experience in the preparation of radioactive sources, was selected to undertake this task. And this is how the standard was deposited at the BIPM on 21st February 1930. You see here the procès-verbal with the first time the radium standard was kept at the BIPM, and on the left, the iron safe where it was placed. The multiplication of laboratory standards made it necessary to adopt an international reference standards. And the international standard would enable each state to own a radium standard, which could be compared directly with the international standard. It was, of course, very important for measurements, which would become more reliable and traceable, both for commercial and health applications. Marie Curie published a paper in 1912 where she explained the reason and the importance of these standards. In this paper, she said, this shows how important it is not to neglect anything that could make the use of electrometric methods for measurement in radioactivity still safer and easier. And I'm thus led to explain how scientists working in the field of radioactivity have been increasingly convinced of the necessity of establishing an international standards for radium and of thereby achieving a significant improvement intending to bring greater clarity and security to the work or the laboratory concerned. So it was important, of course, on the point of view of the science of radioactivity to ensure agreement between the numerical results obtained in different laboratories. And of course, in the event of disagreement, it could also lead to observation of new facts. From the point of view of medical application, it was important by allowing the exact and safe measurement of the intensity of the source of the rays employed. And from the industrial point of view, to provide stability and security to the radium industry by enabling the sale of products whose radium content will be precisely known, thus establishing complete confidence between manufacturers and purchasers. So on this slide, you see the instrument that was built by André de Bierne and Marie Curie to keep the international radium standard at the Curie laboratory. And Marie Curie concluded her paper of 1912, highlighting the usefulness of this future international radium standard. André Allisy pointed out that the first unit used in radioactivity was the unit of mass, as the radium standards were defined by the mass of radium regardless of its state of chemical combination contained in sealed glass tubes that you can see on your left. Why the BIPM was asked to keep this standard? As Vincent just said, the BIPM was established 150 years ago. In 1913, it had 26 member states. And the task of the BIPM was to ensure the international unification and perfection of the metric system. So in 1913, BIPM had activities in mass, length, and temperature, and not, of course, in ionizing radiation. We must say that as from 1881, the BIPM was already foreseen that the BIPM would extend its activity to measurements in the field of electricity and photometry. You see here the safe where the international prototypes of the meter and the kilogram were kept. So it means that in 1913, the BIPM was already recognized as an institution able to produce and keep standards recognized at international level. The reason why the BIPM was asked to keep the first international radium standard was first personal links between Marie Curie and Pierre Curie and Charles-Édouard Guillaume. We also need to mention that between 1900 and 1906, Marie Curie was teaching physics at the École Normale Supérieure in Sèvres, which is just 100 meters from the BIPM, and where some of you may have stayed during this CCRI week because they host many of our participants. In this school, she succeeded to Lucien Poincaré, and so she was teaching at a very close distance of the BIPM. But the main reason was that Charles-Édouard Guillaume and Pierre Curie were very close friends. You can see here on this quote written by Charles-Édouard Guillaume, highlighting his friendship with Pierre Curie. He wrote that in 1920, and he said, "Among those who knew Pierre Curie, I'm one of the oldest. We were contemporaries, our interests and aspirations were similar, and having often exchanged ideas after the meetings of the Physical Society, we became friends. On Sundays, he sometimes came to Sèvres, and I went to Sceaux by bicycle or on foot. We found it very difficult to separate, and more than once, we said goodbye late at night in the middle of the woods of Meudon, each of us going home. His thought infused me like a blessing, and I understood later how much our discussions had guided my evolution." And you see here this photo taken at the BIPM in 1904 by Charles-Édouard Guillaume. On this picture, you can see Marie Curie, the father of Pierre Curie, and Irène Curie at the BIPM in 1904. In practice, you could see also F. Curie, because at that time, Marie Curie was pregnant. On the second photo, you see Charles-Édouard Guillaume and his family. So from the left to the right, so Charles-Édouard Guillaume, le docteur Tripier, Auguste Tripier, who was a physician, former assistant of Claude Bernard, and inventor of the electrotherapy. Maurice Guillaume, the son of Charles-Édouard Guillaume, and the lady next to the boy is Madame Anne Guillaume Tofflib, who was the fourth woman to be hired to work in the lab at the BIPM on thermometry. Behind the father of Pierre Curie, Madame Hélène Dubois, who was a physics teacher in Sèvres, and of course, at the end, Pierre and Marie Curie. At that time, Charles-Édouard Guillaume was deputy director of the BIPM in 1901. 10 years earlier, he had invented INVAR, an alloy that has the property of not expanding under the effect of temperature. He will be awarded the Nobel Prize for that in 1920 for all his research on nickel alloys. Vincent has mentioned Röntgen. I would like just to mention that in 1896, Guillaume wrote a book aimed at the scientific audience, which was entitled X-rays and photography through opaque bodies, published a year after the first work of Wilhelm Röntgen, who was also a close friend of Guillaume. The box containing the photograph of a watch and its chain was published on the frontispiece of the book written by Guillaume. The book was very well received and some papers in La Nature highlighted that. In 1906, Pierre Curie passed away. As you know, he was struck by a horse-drawn carriage while crossing La Rue Dauphine in Paris and was killed instantly. His funeral took place 2 days after. After the death of Pierre Curie, Marie Curie took over his professorship at La Sorbonne, becoming the first woman to teach at university in France. And Guillaume continued to support Marie Curie as one example of the support he provided to her with his friend Camille Onès and many academicians like Gaston Darboux, who was a mathematician and also a CIPM member. He strongly supported the application of Marie Curie to the Academy of Sciences in France. In the end, it was Édouard Branly who was elected with a majority of only 2 votes. And you see in the letter Guillaume sent to Camille Onès to inform him about the results of the election, he said that all that remains is for Madame Curie to be duly recognized by foreign academies. I know from our last conversation that this idea has your full support, so that promoted her application in many foreign academy of sciences. Marie Curie had a sentimental attachment to the radium standard. It appeared convenient both for the International Radium Commission and Marie Curie to ask the BIPM to keep the international standard. The BIPM had 2 main advantages. Of course, Guillaume was a very close friend of Marie Curie, so she trusted him a lot. The seat of the BIPM was at a very convenient distance from the Radium Institute in Paris, and so therefore it would be very easy to collect the radium standard and to run comparison and to place it back at the BIPM. And you see a few papers published in the French press, like Le Temps, which was a newspaper with a very large audience, started to talk about the eventuality of having the international radium standard, like here, the small radium tube, which will serve as the international standards, is likely to be deposited at the Bureau International des Poids et Mesures. The first contacts were first informal. André de Bierne informally wrote to Guillaume on 18 March 1912, before the meeting of the Commission in Paris. And he explained that in order to avoid having to choose between the different radioactivity laboratories, it would be a good idea to be able to deposit the radium standard with the International Bureau of Weights and Measures. Guillaume replied only 3 days after that, after having consulted the director of the BIPM, and gave a principal agreement. He just put some boundary conditions, like the packaging that will be made in such a way as to avoid any liability, of course. And he also stressed that the BIPM would not be able to perform any comparisons on site because the measurements in the field of ionizing radiation were absolutely outside the scope of the BIPM work. So this is why and also that's the reason why the standard was kept in a different safe as the meter and the international meter and prototypes. First, because it had to be available without having to gather the 3 keys to open the vault, and also to prevent any damage. At the time, the knowledge on radium standards was not complete. René Benoit also, so Stephen Meyer wrote in April to René Benoit to ask, this time officially, the BIPM to keep the international radium standard. And René Benoit replied in May, also highlighting some security issues about this standard. In particular, so he reminded Stefan Meyer that the BIPM held great wealth, and in particular with the international prototype and their witnesses. And also, it has to be reminded the cost of the radium standard. The gram of radium, the cost, Marie Curie evaluated it in 1912 to 400,000 francs. So it was very expensive. And in this letter, Benoit stressed the security issues because the BIPM was isolated in the Parc de Saint-Cloud. At that time, the security was only assured by dogs and by 2 guardians. And of course, the BIPM also kept a lot of precious metals. So René Benoit clearly asked the international meter radium standard to keep confidential to all the members that the fact that the BIPM would keep the international standards. On 18 February 1913, André de Bierne announced his venue at the BIPM and said, "We will come to save Madame Curie and I on Friday morning at about 10:30 to deliver the radium standard to you." And this is how the Radium International Standard was deposited at the BIPM on 21st February 1913. This decision was certainly a little bit difficult to her, but the friendship with Charles-Édouard Guillaume played, of course, a very important role. And of course, it was very important for the Commission that this standard would be kept in a very neutral and independent place. As you can see on these letters, Charles-Édouard Guillaume took a very active part in drawing up the rules of the conservation, removal, and return to the safe of the Radium International Standard in close cooperation with André de Bierne and Marie Curie. He suggested some amendments, which were fully accepted both by Marie Curie and Ernest Rutherford. The signature of the members of the International Radium Commission was added on the final version of the rules of the conservation of the international standard. It was a very official document, as you can see, bearing the signature of the most eminent scientists in the field. Ironically, until 1959, the International Radium Standard officially did not exist at the BIPM. It appeared in none of the official reports, and even the CIPM had to investigate in the 1950s to understand how the first international radium standard had been kept during more than 20 years in the BIPM safe. The reasons for that was, as I explained, the BIPM had no activity in the field of ionizing radiation, of course, was not entitled to run comparisons on site, and René Benoit and Guillaume thought wise to keep it confidential, first for the outside world for safety reasons, but also they didn't want to have to ask the CIPM the permission to keep this standard. So they just informed the president of the CIPM, who was Wilhelm Forster, and the secretary of the CIPM, who was at that time Pietro Blazerna, that to have their formal authorization, and it stopped there. The first time the international radium standard was used was to measure the secondary standards for different countries. So the international radium standard was removed for the first time on 8 May 1913 by Marie Curie and André de Bierne for the determination of the standard number 3, which belonged to the National Physical Laboratory in the United Kingdom. You see here on this table, so 11 exactly national radium standards were compared with the international standard at the Laboratoire Curie during a period of 20 years. And you see the last one was in 1933. And of course, the radium content of the standard of the various countries was determined with means of a gamma ray comparison with the international standard, and a certificate was produced accordingly. Marie Curie, as you know, was treated for leukemia and passed away on 24 July 1934. The same year she died, 𝐂𝐚𝐻𝐿 in Vienna performed a new determination of the atomic weight of radium using 3 grams of radium and prepared 20 new radium standards that were made using pitch bundle originating from 𝐂𝐻𝐿𝐻 in the former Belgian Congo and which were practically free of mesothorium. 2 of these standards, number 5428 and number 5430, were of equivalent mass to the Curie standard. And from 1935 to 1939, these 2 new standards were compared with primary and secondary standards. So the standard number 5430 was attributed to France and given to the Laboratoire Curie and replaced the first international radium standard. On 21st April 1939, Frédéric and Irène Joliot-Curie, Frédéric Joliot-Curie was secretary of the commission, and Irène Joliot-Curie transferred the new international standard to the BIPM. And this standard stayed for a very short period of time because in 1940, with the occupation, Perard and Cabrera asked Irène and Frédéric Joliot-Curie to remove it from the BIPM. So as you can see, there was a very important military presence all around the BIPM. You see this sign, Eintrid Verboten, who was applying in the Parc de Saint-Cloud and also on the gate of the BIPM, that the director of that time wanted to be recognized as an international territory to avoid a military occupation. And the BIPM had to protect itself, the standards it was responsible for. You see this disposal, which was made a little bit later in 1942 after the bombing of the Renault factory at 200 meters of the BIPM to protect the international prototype of the kilogram. So for these reasons, on 24 May 1940, Blas Cabrera, who was the CIPM secretary and was living in Paris, asked Irène Joliot-Curie and Frédéric Joliot-Curie to take back the standard, which was removed from the safe a few days later on 30 May 1940. Considering the threat posed by the war, the international standards was moved for security reasons as far as possible from Paris, and the international standard so was kept then between 1940 until 1959 under the responsibility of the Institute of Radium of the University of Paris. So what happened after 1935 to the first international standard, the international standard prepared by Marie Curie? In the archives of the Musée Curie in Paris, it appears that this standard was still used. In 1941, the first international radium standard was sent to PTR in Berlin to be compared by Carl Friedrich Weiss to the Belgian standard number 5431 prepared by 𝐂𝐚𝐻𝐿 in 1934. In 1940, there was a dispute about the precision of the standards, and remeasurement was performed by the PTR by Weiss. The archives of the Curie Museum show that the international standard was back then at the Curie laboratory. We don't know exactly when. We just have a report from Irène Curie stating in 1953 that the first international standard was still stable, and then we completely lost track of this first standard, who was maybe removed like radioactive waste, or we don't know, we absolutely don't know. But this first international radium standard was prepared by Marie Curie, was the basis of the international measurement system for about 50 years, became less important, of course, after the Second World War, but this was the first unofficial activity which started at the BIPM in 1930. The story of the International Radium Standard has been told in a paper published thanks to Brian Zimmerman in Applied Radiation and Isotopes a few years ago. I would like just to mention a few books. So you have The Elements of Marie Curie, which is a recent book written by Dava Sovel. There is a very nice book just published by the Musée Curie in Paris in October 2025. And you can also find, of course, some insights on the history of the BIPM, the radium standard, and Charles-Édouard Guillaume and the Curie family in the book published for the anniversary of the BIPM in May. Thank you very much.
Good morning. I'd like to thank the organizing committee for including me in this session on radionuclide metrology. There's a great deal of history in the first 50 years of radionuclide metrology that precedes the formation of the CCRI. I'll spend most of my time with the activities of the International Radium Standards Commission. The commission was really the forerunner of organizations like the ICRU, the CCRI, and the ICRM. These later organizations built on the protocols developed by the Radium Standards Commission. In the first decade of the 20th century, Ernest Rutherford led a major program in nuclear science at McGill University in Montreal. He did this in collaboration with his colleagues in the physics department, Arthur Eve, and with 4 extraordinary chemists. Frederick Soddy from Glasgow and Otto Hahn from Berlin spent time at McGill. And Rutherford struck up a collaboration with the American chemist Bertram Boltwood at Yale University. Boltwood had graduate studies at Munich and later translated some German textbooks into English. One of Boltwood's collaborators on measurements of the half-life of radium-226 was Ellen Gleidisch, a Norwegian chemist who took a year away from her studies with Marie Curie at the Sorbonne. The U.S. National Bureau of Standards, NIST today, was only established in 1901. So radionuclide metrology didn't really start for another decade. In the first decade, the few physicists at NBS concentrated on weights and measures under the direction of the director, Samuel Wesley Stratton, and electrical standards led by the deputy director, Edward Rosé. In 1907, Rosé and his younger colleague, Noah Dorsey, made the most accurate measurements at the time of the speed of light. But the few NBS physicists had frequent contact with Rutherford and Boltwood at meetings of the American Physical Society, and Rutherford made 2 visits to NBS in Washington. About 1910, Rosé assigned Dorsey to plan for receipt of a standard of radium. Much of the information we have comes from a series of 18 letters that Dorsey exchanged with Boltwood. The International Congress on Radiology and Electricity met in Brussels in 1910. They appointed an International Radium Standards Commission of 10 scientists who are working in the new field of radioactivity. 2 of them were the Nobel Prize winners, Marie Curie from Paris and Ernest Rutherford from Manchester University in England. The third key member was Stefan Meyer, who's the director of the Institute for Radium Research in Vienna, was appointed secretary. You'll notice that 4 of the members, Soddy, Hahn, Eve, and Boltwood, were Rutherford's collaborators from his days at McGill. Marie Curie was joined by her colleague, André Debierne, and Stefan Meyer by his colleague, Egon von Schweidler. The 10th member was Hans Geitel, who was active in radioactivity measurements at a school in Wolfenbüttel near Braunschweig. The commission had 3 assignments: to establish the quantity and unit for measurements of radioactivity, the Curie, which represented the activity of radon-222 daughter in equilibrium with 1 gram of radium-226. I'll leave the discussion about quantities and units to talk later in this session. Secondly, they were to prepare standards based on mass in Paris and Vienna. And third, the commission would certify secondary standards that could be used to calibrate radium in nations around the world. Marie Curie prepared the primary standards Céline has shown of 21.99 milligrams of radium chloride, and Otto Hernigschmidt prepared secondary standards. In March of 1912, 7 members of the commission met in Paris, where Rutherford and Debierne used separate instruments to compare the Paris and Vienna standards. They were found to agree to within 0.2%. Then in 1912 and 13, Hernigschmidt prepared 7 standards to be measured in Vienna and Paris and distributed to several countries. This slide is from a 1912 paper in German by Meyer and Hess that lists 5 standards that Hernigschmidt had prepared. Only the standard listed here is number 2 at 31 milligrams was used for the intercomparison with Curie's standard in Paris. I think it's remarkable that Hernigschmidt had over 0.5 gram of radium that he used for the measurement of the atomic weight before he subdivided it into these 5 standards. Meyer's co-author here is Victor Hess, who designed ionization chambers that were used in Vienna to compare the 3 smaller sources. That ion chamber looks very much like the primary ionization chamber today. During the same time he was measuring the standards, Hess discovered a residual background in his ion chamber measurements. He followed this up by making some balloon ascents in which he discovered cosmic rays. For this, he shared the Nobel Prize in Physics in 1936. This table is the first of 7 international standards from a German textbook on radioactivity by Stefan Meyer and his colleague Egon von Schweidler. The first standard of 22.47 milligrams was provided to the Curie Institute to replace the 21.99 milligrams that Marie Curie had agreed would remain at the BIPM. Céline has talked about Marie Curie's decision to allow the standard to be kept at Sèvres. The Physikalische Technische Reichsanstalt in Berlin and the National Physical Laboratory in Teddington also received the 1912 standards. The US standard was in the second set of standards certified in 1913 and was not received in Washington until Christmas of 1913. Noah Ernest Dorsey was given the assignment to design a national radium calibration service for the United States. Dorsey jumped into his new assignment. He met with Boltwood at Yale and with Dr. Robert Abbey, a radium physician in New York. He then traveled to Pittsburgh, Pennsylvania to learn as much as he could from the chemists and physicists at the Standard Chemical Company and purchased 2 standards, a 1 milligram and a 4 milligram of radium sulfate. He set up an electroscope and made measurements of the radium standards from Pittsburgh and reported to Boltwood that he obtained good agreement using the Rutherford method for comparing radium sources. This slide shows a certificate for US standard number 6 signed by Curie, Rutherford, and Meyer. The upper quadrant is discolored because at some point it was contaminated with a radium solution, and it contaminated all the other records that are from that period, including Dorsey's small notebook. Lisa mentioned that earlier, that all of these documents are now contaminated papers, but they're safely stored. This note on the right is from Dorsey's comments when he first examined it in Christmas of 1913. The Standard Chemical Company in Pittsburgh, Pennsylvania was formed by industrialists who were mining and refining vanadium for the US steel mills. They established mines in Western United States to extract carnotite ore and transport it east to separate the radium. They had early chemistry consultants, including Boltwood at Yale, but their major advance came when the chemist Otto Brill came from Meyer's laboratory in Vienna and designed their radium purification procedures. Brill took a small sample of radium to Paris for standardization in the Curie laboratory. The second chief chemist at the Standard Chemical Company was Glenn Kammer, who handled an extraordinarily large amount of radium, but didn't have much regard for radiation safety. He's shown here tubing 1 gram of radium into glass ampules. In 1914, he sailed to the UK with 4 grams of radium in this lead-lined valise. The radium was intended for UK hospitals, but the hospitals would not accept the radium without assurances from NPL that it was free of mesothorium, that is the shorter live radium-228. NPL didn't have the capability to make such measurements, so they contracted with a chemistry professor, R.J. Strutt. who provided NPL with assurance that the material was free of radium-228. For some reason, we have copies of all this NPL correspondence, which is, of course, contaminated like everything else from that decade. Cameron, by the way, died of radium poisoning at age 39. The United States provided most of the world's supply of radium from 1912 through the end of World War I. That was due in part to the disruption in Europe from the war. The radium was, as I mentioned, came from carnotite ores that were processed in Pittsburgh for sales in the US and overseas. Essentially, all the sources for sale were calibrated at NBS using International Radium Standard No. 6. The high point for radium in North America came when Marie Curie visited the US in May of 1921 to receive a gram of radium that had been paid for by donations from the women of America. She received the radium in a ceremony with President Harding at the White House. The following Sunday morning, she and her daughter Irene visited NBS to inspect the source and the instruments and methods used at NBS. Curie then visited the factory in Pittsburgh where a camera had prepared the gram of radium. This photo of Marie Curie in the Pittsburgh newspaper means a lot to me because I found the image, I found this picture 40 years ago on top of, in a cheap frame on top of a file cabinet. 70 years after her visit to NBS, there was nothing in the NIST archives that indicated that Marie Curie had ever visited our institute, and I've been looking into this ever since. The certificate for Marie Curie's gram of radium was designed by a special engraver and signed by the director of the Bureau of Standards. It was packaged as 10 ampules of nominally 101 milligrams each. These were calibrated at NBS by comparison with a gold leaf electroscope against a 100 milligram working standard that had been calibrated using International Standard No. 6. I think this is important because gram quantities were being sold to hospitals, and it shows, at least in the US, these were packaged in 100 milligram lots that could be standardized to within about 2%. This is very important when the price of radium was over $100,000 per gram, which would be about $2 million per gram today. The radioactivity group at NIST today is a direct descendant of the NBS radium section, formed in 1914. The staffing level was similar, but there are a lot more PhDs today. The staff in those days was nearly overwhelmed by the need to receive, calibrate, package, and ship huge numbers of radium sources for domestic and international sales. This began as a half gram in the first half year until by 1920, they were performing over 2,000 calibrations annually for over 30 grams of radium. After World War I, there were major changes in the radium industry. Before the war, copper mines in the Belgian Congo had been recognized as a source of radium from pitchblende. These were not only richer sources of radium, but the labor and transportation costs were much lower in the Belgian Congo than in the US. The US company recognized this and entered into a partnership with the Union Minière du Haut-Katanga, or UMHD, and chemists from Pittsburgh assisted in the setup of a radium factory in Olden, Belgium, about 40 kilometers east of Antwerp. The Belgian company soon had secondary standards traceable to the international standards. There were limited efforts in the 1920s to prepare additional national standards that Céline showed earlier that were certified by the International Radium Standards Commission. But the big change in terms of the international standards came with the deaths of Marie Curie in 1935 and Ernest Rutherford in 1937. I'll mention first the major changes at NBS. Leon Francis Curtis was a physicist who had spent 4 years on a fellowship with Rutherford at the Cavendish Lab in Cambridge. He built several new instruments, including the primary gold leaf electroscope, which we still have today. Curtis continued collaboration with Lord Rutherford, and he, along with his predecessor, Noah Dorsey, promoted the Rutherford unit of activity, where 1 Rutherford is equivalent to 1 megabecquerel. Many records in the NIST archives give activities in units of Rutherfords or millirutherfords per gram of solution. Constance Torrey, shown here with a radium calibration range, spent 30 years at NBS. She was later identified as chief of the radium calibration service. We're still very much indebted to Céline for the information on the status of the International Radium Standards Commission in the second and third decades. This really cool page from the notebook that Céline located at BIPM lists the approved signatures of the distinguished scientists, who as members of the commission had access to the primary standard retained at the BIPM. From this page, we can construct a list of the members of the commission after the deaths of Marie Curie and Ernest Rutherford. This page indicates that Stefan Meyer at the Institute for Radium Research was the president of the commission. Here are the photos of the 6 members who continued to serve the commission after 25 years. Of course, they were early career scientists back in 1910, but by the 1930s, each led a major program in nuclear sciences. Frederick Soddy had received a Nobel Prize in chemistry for the discovery of isotopes, and Otto Hahn would later also receive a Nobel in chemistry. Here are the photos of 7 new members of the commission in the late 1930s. Irene Joliet Curie took the place of her mother in 1934. She and her husband, Frederick, had major responsibilities for the radium standards. Of course, Otto Hahn-Schmidt was an obvious choice for the commission, given that he had prepared all the secondary standards that served as national standards countries around the world. Chadwick and Geiger had worked with Rutherford in Manchester before the First World War. In fact, Rutherford had Chadwick doing a fellowship with Geiger in Berlin when the war broke out in 1914. Chadwick then spent the rest of the year interned in a relatively civil prison camp for English students, and Geiger looked in on him when he had time off from his duties as a cavalry officer. Samuel Lind was the only U.S. representative. Lind was a chemistry professor at Minnesota who had worked with Marie Curie in Paris on radon measurements. I was surprised to see Auguste Piccard, since I cannot find that he ever did any work with radium, but Piccard was quite famous at the time. He was a member of the 1933 Solvay Conference along with Marie Curie, Rutherford, and Einstein. He had set world records for altitude in balloon flights, and with his twin brother, records for unmanned ocean dives. I know this slide's kind of an eye chart, but it's really important in understanding the 30 standards that Meyer certified in Vienna. Meyer published this table in an Austrian journal in 1945 at the end of World War II. It's very convenient to break it into 2 parts. So I'll show you the first. This table shows 9 standards prepared by Hörnig-Schmidt in 1912 and 1913. Those were the Roman numerals, or those that were certified by were also measured in Paris and were certified by the commission. Standard number 4 here went to Dr. Alton, who was the director of the London Radium Institute, a major cancer institute promoted by King Edward VII. Soddy and Ramsey were on the scientific advisors for that center. The smaller standard number 5 went to the Standards Chemical Company in Pittsburgh, the radium factory that had a standard a year before the U.S. standard number 6 arrived in Washington, and they used it to calibrate the sources for NBS. This is the bottom half of the table. There's a great deal of useful information here. Again, the complete column shows the masses of radium chloride measured in Vienna. Only 8 of these 20 standards were also measured in Paris and certified by the Radium Standards Commission. Number 10 to Denmark and number 18 to Professor Swartenmacher probably went to hospitals in Denmark and the Netherlands. Nearly 0.5 gram of standards in 1922 went to Soddy in the UK. The Radium Institute in Vienna was suffering financially after World War I, and Frederick Soddy arranged for his wealthy father-in-law to purchase a large amount of radium from Vienna at a good price. From 1924 to 1932, 6 more standards went to Belgium, Czechoslovakia, Russia, Australia, and Canada, and their measurements by Marie Curie in Paris were captured in the logbook that Céline showed. The larger standard sources for Belgium went to the Union Minière, or UMHT, in Belgium. The final 2 sources on this list for the USA are in fact part of the set of 20 standards that Hörnig-Schmidt prepared in 1934. This slide shows the certificate for the larger of the 2 standards that came to NBS. The one signed near the end of 1936 was by Irene Joliet Curie. Marie Curie was still living when the Hörnig-Schmidt prepared these sources, but Irene signed all the certificates for the later sources. In the late 1950s, before there was a CCRI Section 2 and before there was an ICRM, many of those who would form CCRI Section 2 were part of the ICRU Subcommittee on Radioactivity. This table is taken from a 1958 report to the ICRU subcommittee by W.E. Perry at the National Physical Laboratory. Perry wanted it on record in one place that Paris and Vienna had provided measurements that were in fact in good agreement on 13 of the numbered standards by the Radium Standards Commission. This summarized measurements made between 1912 and 1932. Wilfred Mann at NBS gave this summary table in a paper at the formative meeting of the ICRM in 1972 in Herceg-Novi. Every National Measurements Institute that had access to more than one of the Herning-Schmidt standards felt compelled to compare the standards and see if they agreed with the values given on the certificates from the Radium Standards Commission. Methods used included electroscopes, calorimeters, ionization chambers, GEM and scintillation counters, and even emanation measurements. At NBS, Mann was able to compare standards from Germany, UK, Canada, and the US. PTB and NPL measured some of these same standards in Braunschweig and Teddington. Peter Christmas at NPL also carried out in a comparison with the Russian standards laboratory Vanim in St. Petersburg. Perhaps not surprising, all these measurements confirm the mass assignments given on the certificates. In 1951, Wilfred Mann at NBS came from the NRC in Chalk River, Canada, where he had been for 2 years. He had been making calorimetry measurements at the NRC. In 1954, he built an NBS twin-cut microcalorimeter to compare several of the Herning-Schmidt standards. This image shows our two standards and from 1934 and the German national standards. The calorimeter was particularly useful for measurements of the 1932 Canadian standards, since it was in a different configuration. Mann was collaborating with Klaus Geiger at Chalk River, who was the son of Hans Geiger from Berlin. The U.S. dosimetry group also made measurements at a distance with the gold leaf electroscope. But in this case, the sources had to be arranged perpendicular to the beam with the radium chloride crystals uniformly distributed in the glass ampules. These were some of the last measurements made with the U.S. sources. Mann designed special brass containers for the two sources and the one from 1913. And these have not been opened for the last 70 years. David Smith and Peter Christmas were the last to try to locate the whereabouts of the 20 international standards in 1989. This table is a summary of measurements received from a questionnaire distributed by David Smith and Nikolai Kormelitsyn from Vanim in St. Petersburg. There were a number of blanks at the time, sources that could not be accounted for. By this time, few of the standards were actually being used. The U.S. standards had not been used for over 30 years. Many institutes considered them too hazardous to be safely stored and of no further use. The radium factories from the early years in Pittsburgh and Belgium were contaminated waste sites. The Belgians had transferred some of their materials to Buchler Corporation, which later became Amersham Buchler and is today Eckert-Ziegler at the same site in Braunschweig. Today, I can only really account for two of these sources. Number 5437 and 5440 are still safely stored at NIST in Gaithersburg. I'm not sure about the fate of the ones in St. Petersburg. And finally, thank you for your attention this morning. I wish I could be there with you in person. I've tried to summarize the saga of the International Radium Standards, an effort that engaged at least some of the time of 9 Nobel Prize winners spanning over half a century. That's a lot to cover in 20 minutes. I'd like to acknowledge these special folks who have provided the materials for this talk. And lastly, I want to join all of you in celebrating the 150th anniversary of the BIPM and the contributions to radionuclide metrology by Albrecht Ritz and Jörg Müller and Guy Rittel and our other colleagues at the BIPM. Thank you.
Okay, so it's a pleasure for me to present the history of ionizing radiation related quantities in the name of the ICRU. I will repeat things that have already been presented because it's I think more or less the same subject. So Wilhelm, not William Röntgen, discovered the X-rays in 1895, and maybe you don't know, but he did not file a patent because he wanted his discovery to be distributed as fast as possible and for everybody. So I think this is something that we have to remind in our time. Becquerel, he discovered radioactivity just 4 months after, not just 1 year afterward. It was just 4 months after. So you can see the emulation that was at that time. And he made his discovery almost by chance, actually. And it was also an almost by chance discovery of Wilhelm Röntgen. So I think this is quite interesting. And he was the discoverer, but Marie Curie is known for radioactivity because she did a lot. She did not just discover, she did quite a lot to develop the science. That's why she's really well known for that. And just to have a broad idea of the main points of the units, in actually exactly 100 years ago, the ICRU was funded in London, and this year in March we did actually celebrate the 100th anniversary. And 3 years afterward, the ICRP, or the ancestor of the ICRP, was funded in Stockholm, in Sweden. And another important event is 1975. I called it Annus Mirabilis. I don't know, maybe it's a bit too much, but that's the time when our units were entered in the SI. So there were the Becquerel, the Gray, and the dose equivalent entered just 4 years after. But I think that's an important moment. So I could stop my presentation here, I think, but but I was allowed to have 20 minutes. So I wanted to just to show you the timeline of the different subjects. So activity, we talked a lot about it. 1910, I think we heard more than I knew actually by myself. That's when the Curie was established. It's quite amazing to realize that somebody had her name in a unit when she was still alive. Usually you get this kind of recognition quite after you're dead. So it's well you're dead. And I think that's quite interesting. And we also said that this was done in the International Congress of Radiology and Electricity. It shows the link with Röntgen. Electricity, we need electricity to have X-rays, radiology, and usually we don't use radioactivity to do radiology, but that was the Congress. And when we look at the report of this, if we enlarge it, we see Curie and Rutherford together. Well, it's not by chance, definitely. And maybe you don't know, but in 1946, somebody, Rutherford was dead at that time. Somebody proposed to have a new definition of the activity, or new unit, which was independent of a sample, and it was called the Rutherford, and it was more or less, not more or less, exactly one megabecquerel. So that was it. It was actually used in the US and the UK, but not really widely used, because as you know, and as I said before, the Becquerel was entered the SI in 1975. And it's interesting to look at the consideration. Why? Because when we have a new unit, we have to explain why we need it. And we see that it's because of the danger, because the second was already defined. So why did we need to have a specific unit? We had to justify in order to be able to enter the SI. Okay, and Curie already had the unit. They would need to change. So maybe they would have done it the other way if they had the chance to really decide who deserves to have his or her name given to a unit. I think they would have chosen Curie in 75, but they had to do it the other way. Another domain in our field is conversion of energy. Actually, the first measurement we did was with a film. We did. Röntgen did, actually. This picture is quite famous. There are a lot of reasons to do that at that time, because photography was already quite well advanced, and it allowed to do quite a lot of interesting things, I think. And the exposure unit was actually proposed in 1928. It was relatively limited from our point of view in the 21st century, because it could only be used for X-rays and gamma rays and for a mass of air. But anyway, it was really useful, and it lasted quite a long time. The definition, as you can see here, maybe I should. No, I cannot do it. Maybe if you look at the definition of the unit, 1 Röntgen is 1 ESU per this amount of gram. So it seems a bit weird. from our point of view, but it makes sense because at that time the ESU was the electrostatic unit, so it was defined by the force of two charges of the same same amount at 1 centimeter distance that produced a force of 1 din. Okay, complicated, but anyway, it was useful. And this quantity here, it seems a bit weird, but it's actually the mass of 1 cubic centimeter of air. So that's why it was defined like this. In the 1960s, the concept of energy transfer arose because people realized that exposure was a measure of ionization in air, but it was hard to make a connection with the effect in tissues. So they had to find something different. And actually, the 𝐏𝐬𝐬 in air was defined by the ICRU in 1969. I was already alive at that time, and it was developed and more adopted in the following years. And right now, at least, I'm sure there are a lot of other users, but it's really used in medicine, in radiography. When we want to know what is the amount of radiation in air at a given position, we use the air camera. Deposition of energy. That's something that is also very important when we want to know the effect of ionizing radiation. Actually, this concept started to be analyzed or thought about in the 1940s by Maynard and Gray, because they were doing radiobiological studies, and they needed to have a physical quantity that could be used and to interpret their result and understand what was happening. In 1945, Parker proposed a unit for what was not called the absorbed dose at that time. It was called the energy absorbed per unit mass. And they proposed to have a unit which was called the Röntgen equivalent physical. So you see, the Röntgen unit was still really useful at that time. And actually, the absorbed dose, as we know it, was developed within the American NCRP, and then also within the ICRU. And this is the definition of what we currently know, more or less, the energy deposited per unit of mass. And the big advantage of this compared to the Röntgen is that you can define it for any kind of material, any kind of tissues, for instance, for any also radiation. And the definition was 1 erg per gram, so energy per unit of mass. And well, here you have the connection with the quantity we have now. And this is a fundamental quantity that correlates to many biological effects. It's actually still used in some countries, or maybe in one country, I don't know. It's used also in any radiotherapy department. I don't know if you're aware of that, but because in radiation therapy, they like to use the monitor unit, and there are 100 monitor unit in 1 gray. So in a way, they are still using the rad in any radiotherapy department. 75, I already said that the gray entered the SI. The justification was the same as for the Becquerel, and obviously Gray was chosen because he was one of the fathers of the absorbed dose, and he did a lot of work in radiobiology, and I think it was quite straightforward to propose his name for this quantity. And also Gray had a lot of contact with ICRU. He worked a lot with ICRU. Biological dimension. We had this question before: when did we know that ionizing radiation was dangerous for the health? Actually, we knew it from the very beginning, more or less. In 1902, the first limit, well, it was not called limit at that time, but the first thing related to biology was actually defined as the erythema dose. So the dose, the quantity of radiation necessary to produce an erythema. And actually in 1906, the laws of Bergonier-Tribondeau, the two very famous medical doctors, they already understood why, or maybe which kind of cells were sensitive to radiation, those which multiplied a lot. Well, they knew quite a lot in 1906 already, and they treated patients with radiation at that time. In 1927, the heritable mutation were actually already observed in flies, in Drosophila. They didn't know about the structure of DNA at that time. And that actually helped in the 1930s and 40s to have some kind of protection limits that were lowered because of this kind of discovery. They didn't think about cancer, but they were really concerned about genetic effects. And you can actually see that when you ask somebody who doesn't know anything about ionizing radiation and you tell the person, well, be careful, there are radiation. What do they do spontaneously? They do that. So they understand that there are some heritable effects, I think. In 1945, it was shown that DNA carried genetic information. The double helix structure of DNA was discovered 9 years afterward. And for us, I think one of the most important event to know a bit more about the effect of ionizing radiation was the bombing of Hiroshima and Nagasaki. Soon after, they saw that people started to have more leukemia, more thyroid cancer, breast cancer, solid cancers, excess of multiple organ cancers were really strongly established in the 1970s and right now. And maybe you don't know, but cardiovascular disease are now quite acknowledged. That's something that it is discussed now. And there are still a lot of people still alive from the Hiroshima and Nagasaki cohort, and they have more cardiovascular problems than the population that was not exposed. At that time, 1940s, 50s, people realized that the absorbed dose was not sufficient to really understand the effect of ionizing radiation, because different kinds of radiation did have different effects for the same absorbed dose. So that's why in 1954 the quantity dose equivalent was actually proposed. And how was it defined? It's actually the absorbed dose multiplied by what we call the relative biological efficiency. And what is interesting to realize is that the name of this quantity for the dose equivalent is the REM. And you may have said or thought that it was the rad equivalent man, but it's not the rad equivalent man. It was the Röntgen equivalent man. And it's not for nothing. It's because actually the REM was defined before the RAD, because people understood the effect of biology before they really developed the concept of absorbed dose. So it was done in parallel, but the RAD was defined just after the REM. That's why it's the Röntgen equivalent man. Okay. 1958 is an important year for the ICRP. It was the first publication of ICRP. It consolidated the system. It was really a milestone, I think, for radiation protection. And actually, before 1958, only tissue reactions were considered. And in particular, because of Hiroshima and Nagasaki and the discovery in genetics, after 1958, also the stochastic effect encompasses heritable effect, but mainly cancer. In 1977, the ICRP proposed a way to put the dose equivalent in different organs together. And they realized that different organs had different sensitivities. And therefore, they had to find a new name, not dose equivalent, but because they had to mix all the different organs, they called it effective dose equivalent. And the definition was made like this. So they made a weighted summation of all the organs or all the tissues, if you want, and each tissue had a different weighting factor. And they took into account the absorbed dose in these tissues, and they had to in order to have dose equivalent, they had what they call quality factors. And the quality factors were defined according to the linear energy transfer. Well, I don't want to go into too much details, but anyway, the unit that was chosen for the effective dose equivalent was the sievert, and in basic units, it's a joule per kilogram. But if we read the publication 26 of ICRP, we see that the REM was still quite present, because in every pages when they talk about the sievert, in parentheses, they put the value in REM just to make sure that people understand what it means. In 1979, as I already said, the unit sievert entered the SI as being the dose equivalent. And it's funny to read the considering of why they accepted to have a new unit called sievert, because actually there isn't maybe no reason. We already had the gray, and we could have maybe continued like this in the SI, but they took a lot of precaution. You see, usually we don't like special name. We try to avoid it as much as possible. But anyway, well, for ionizing radiation, we will do an exception. But please do not come back and ask other exceptions if we read this. That's the way I understood it. And the definition of the equivalent dose is the absorbed dose multiplied by the quality factor and multiplied by factor n, which was here just to make sure if something else happened, we can enter it and multiply to make an additional correction. And the unit, well, that's how it is. Okay. And they give the name to Rolf Maximilian Sievert. He was actually a founder of ICRP, and he was the chair of ICRP when publication 1 went out. So he was really one of the most important person in radiation protection. I think that's quite clear. In 2002, there was a revision of the sievert. I don't know if you're aware of it. In recommendation 2 in the 1991 meeting of the CIPM, and as I said, the definition of the dose equivalent was this, and in this revision they proposed to discard the n. And actually, when you read the consideration, they said that they did this change because the ICRP and the ICRU were not satisfied with that. So it was a proposition of ICRU and ICRP to get rid of the n factor. Just before, in 1991, the effective dose was actually defined. It was no more the effective dose equivalent. It was called, to have something shorter, the effective dose, just like this. So there was a reevaluation of the weighting tissue factor, and there was also a change of HT. HT within ICRP is no more the dose equivalent, is the equivalent dose. So if you ask people in the street, what is the difference between equivalent dose and dose equivalent, obviously nobody will understand even the question. But even in this room, I presume that some people may struggle to explain the difference between those two quantities. And actually the main difference is that the quality factor, QL, which was used to define the dose equivalent, is no more used in the equivalent dose, is WR. WR, the weighting factor for the radiation, it's more or less compatible. It's based actually on RBE, relative biological efficiencies, and it accounts for stochastic effect at low dose. It's broadly compatible with the Q factor, but not totally. And here you have the values that are more simple than the Q of L values that have to be computed in on average in the tissue. So it makes things simpler. And actually this was well explained in ICRU report 51, in which the dose equivalent had this definition and the equivalent dose had this definition. And you can clearly see why it is simpler, at least for the equivalent dose. This actually makes a good transition for the operational quantities, which were defined by ICRU 40 years ago, actually. The quantity that you most likely know are the quantities that are measured by your dose meters, HP10. If you are wearing a dose meter, normally it should measure HP10 or most likely also HP007. And if you want to measure the dose to your eye lens, you also have a dose meter calibrated into HP3. Or if you have an ambient dose meter, this kind of dose meter, it will most likely be calibrated in terms of H*10. So these are the operational quantities. And the operational quantities, they are measurable. That's their main advantage and their purpose. It's not their only purpose. They are also supposed to estimate the protection quantities, the effective dose, the dose to the skin, the dose to the eye lens. That's the whole point of having operational quantities that are measurable. Unfortunately, if you look at what happens for the population that is the most exposed to ionizing radiation, people working in radiology, they account for 80% of the population, 80% of the collective dose. It doesn't work that great, actually, because if you look at these people and you try to you measure HP10 and you look at the precision is great. When you want to estimate the effective dose, the precision of this quantity is great, but it's a factor when you are in the area of 30, 40 kilo electron volt. It's very precise, but the accuracy is a factor 2 or 3 away from the quantity. It's actually overestimating the dose. So that's actually why ICRU report 95 was written mainly by ICRU, but endorsed also by ICRP, which propose new quantities that are still measurable, but they are no more defined on these rough phantoms that you just saw. They are defined the same way as the protection quantities are defined, with phantoms representing reference humans. And actually they do provide quite a good estimate of the protection quantities. And in particular, if you look at HP, it's no more HP10, but it's HP for the whole body. It's actually a bit less precise, but it's much more accurate. And so you see the difference. And that's just right now that we haven't really started to develop new measuring instrument. So what is the future for the quantities? I think we have very solid quantities and units right now that do quite a great work for the population, for all the fields that were already mentioned, actually. What I see as something that is not really coherent is the definition of the sievert, because the dose equivalent is no more used neither by ICRU, neither by ICRP. It's now only defined regarding the effective dose. Now we have ICRP, ICRU, who uses the sievert related to effective dose, and we have in the SI system the sievert which is related to a quantity dose equivalent, which is no more recommended. So I think now we are 25 more a quarter of a century after the last change of 2002, we would need to ask to update the definition of the sievert, and that's something that should come back here at BIPM one day or another. Okay, so I thank you very much for your attention.
So I should thank Vincent very much for inviting me to give this talk a year ago when it seemed a long time away, and so I said yes, rather rashly. So here I am, having arrived last night at midnight. So if I fall asleep during my talk, you have all my sympathy. This is really a homage to André Allisy, without whom the Department of Ionizing Radiation at the BIPM would not be the way it is today. André graduated in 1945 and worked in the research laboratories of Yves Rochard of the École Normale Supérieure in Paris. During the first 5 years that he was there, he had a project to work on how on earth you should measure ionizing radiation. There was nothing in France at that time to be able to do it. So he set about creating the first free air chamber for France, effectively. Once he'd done that, he compared it with the NBS, or the NIST as it's now called. And when he compared it with the NBS, he got very good results, and he realized that the NBS's free air chamber had actually been constructed by the French industry, Mesures, with whom André also had contacts. So it was a circular type of thing, if you like. And then in 1950, a French radiologist attended the ICRU meeting in London, I think it was. And when he came back, he said to Mesures, I didn't understand a word of what they were talking about. Do you have anybody who knows about this domain who could actually go in my place? So in 1953, André was sent to the ICRU, where he already knew some of the people because of the work he'd done at the NBS. and he was welcomed with open arms because he had read all their scientific papers. And I think that says a lot for the type of man he was. And Andre became a member, obviously, of the ICRU. He eventually became president of the ICRU. I think he was president for 12 years. I'm not quite sure, it might have been less. And he was given honorary membership on his retirement from ICRU. So you could say that his life was ICRU, apart from everything else that he did. Because of his presence on ICRU, he was at the very first meeting of the CCRI, which is the Consultative Committee for Étalonnage, Mesures, and Rayonnement Ionisant, or however you like to pronounce it. I'm sure Vincent would do it much better. So he was there at the start. And let me just get my thoughts straight on this, because the CCRI was actually proposed to be set up by the BIPM, by the ICRU and the NBS combined. So it was the NBS representative on the CIPM who said, really, we need to have something about ionizing radiation at the BIPM. We need to start with the Consultative Committee to see what's needed. So they set up the CCRI. And because of Andre's position at ICRU and his work on standards in France, he was actually the first effectively executive secretary, or secretary as it was at that time. So right from the beginning of that work here he was. And this is one of my favorite photos of him, because with all that paperwork on his desk, I felt so much at home. So the CCRI was set up in 1959, and this is the first photo, or the photograph of their first meeting. And their first proposal or resolution to take forward to the CIPM and then the CGPM, and I'm not going to spell them out because you've already heard what they are, was that the BIPM should set up a section for ionizing radiation. So that went to the CGPM and they approved it in their October meeting of 1960. And so in 1961, the RI section was set up. So the first thing they needed was somebody to run it. So they advertised and they got somebody in post, but that didn't work out because the person never came to France. So that fell through, and Thérion, who was the director of the BIPM at the time, turned around to André Allisy and said, what would you recommend? What would you do if you were setting up an RI section at the BIPM? So André came up with a plan. He needed laboratories, he needed equipment, and he needed a budget, and he needed staff, and all of that was put forward. And guess what? He was appointed head of the RI section. So over here in the plan, you can see this was the RI building that we now have. This is actually the Pavillon de Maille, but I'll talk about that later. And you can see that the BIPM actually finished about here in those days. So they had to extend the land that they had with the accordance of the French government, so to be able to build the buildings. So that was a major step forward. Things were much easier in those days. Don't think that would be quite so easy these days. And André was effectively then a laboratory designer. He had to come up with what he wanted in terms of the building. And no buildings start immediately. So here we go. You have to dig holes, you have to have foundations and all the rest. And slowly the buildings were put in place. Now this is remarkably quick. The section was set up in 61, and from 62 to 64, the buildings were going up and were completed in 64. So this is the dosimetry activity and then alpha work in the building that is still opposite us, which you may or may not have visited. And at the same time, a neutron building was put up. And here's the foundations of the neutron building, and here it is. And we're now in the building that replaced it. And I'll explain that a bit later. So this is how the buildings looked in 1964 when they were finished. Dosimetry comparisons were started immediately. André wasted no time. He had colleagues that he brought with him from his research lab to start the work. and employed others. And we had a free air chamber for low energy X-ray comparisons almost immediately. And if you go over to the RI section, you can see a poster that Cecilia's put together showing the evolution of all the dosimetry standards in the RI department. And of course, activity comparisons took place as well for pi beta gamma counting to start with. SIR, which, do I need to explain what that is to this audience? Système International de Rayonnement. Référence, merci. Do you see, I've been retired too long and my memory is not what it was. Not that it ever was very much. So there we are, that's the SIR. And we had neutron comparisons in those days with the manganese bath and other equipment. And I'm going to say that the neutron work stopped when the scientific expert in that field here, Poids, retired. And at that stage, the director of the Bureau said, look, we don't need to replace him. No one's using neutrons anymore. What do we need neutron measurements for? So it was stopped. However, the SEMRI, because it was covering so many wide fields of ionizing radiation, because those who are expert in activity measurements don't necessarily know about neutrons, don't necessarily know about dosimetry, the SEMRI was actually split up into 4 sections. So section 1 was for dosimetry, and that met in May 72. Section 2 for activity met in the September. Section 3 for neutrons, and I'm sure those of you from the NIST will recognize this person, was in April. And section 4 was for alphas. And here's Jörg Müller, who was mentioned earlier, great mathematician. So really, the reason they split it up was because the people who came originally to the CCRI, or SEMRI as it was then, came from the National Measurement Institutes, but they weren't necessarily expert in all the fields. So for a third or even a quarter of the meeting, they were bored out of their minds. So the idea was to have 3 separate meetings so people could really concentrate on their expert field. And luckily, I think we've come back to that today, which is lovely. So that's how it was. At the same time as all that was going on, of course, we have dosimetry comparisons going on. And here's our medium energy free air chamber. And here's one of the results from those comparisons. I did try to get a bit more information from the BIPM website to show you a few more things like this, but I found it extraordinarily difficult to do. When I was working here, and actually I should go back to 1994, I think, might have been 95, when the internet came to the BIPM. And our then director, sorry, not director, our then head of section was not very keen on this idea. So we had to fight to have 1 point in our building. But once we had 1 point and we could actually communicate with all the NMIs at any time of day or night, and they'd find the message when they woke up, I think the understanding was this is the way forward. And of course, that's what led to the MRA being able to be enabled, because without communication, you can't do it. That's what enabled the KCDB, the Key Comparison Database, to be set up. So it all stems back from that time. Obviously, activity comparisons continued. Then we have cobalt-60 sources, which we've had to replace twice. This is the latest one, and I believe it needs to be replaced again now because cobalt-60 decays quite quickly, and it becomes a stage when you can't actually measure anything sensibly. And so I'm going to move on quickly to the CCRI. Now, the CCRI was the shortened name for the SEMRI. So this is just the Consultative Committee for Ionizing Radiation, or Rayonnement Ionisant. And that was, the name change was made in 97. And that was under the presidency of Prof. Boscati. I should have said that each president of a CC is actually a member of the CIPM. I'm not quite sure how the CIPM decides who's going to be the president. Perhaps Dr. Janssen will be able to tell us whether they're volunteers or whether they're arm twisted. Prof. Moscati, it was great fun. And he was instigating for the name change and also to use end users in the CCRI. So this was the composition of the CCRI, half of which looks as if it's members of the section, and then some specialists from NMIs and some end users. By the 18th CCRI in 2003, Giorgio, this is Moscati here, had decided we only needed the section chairman on the CCRI, because the section chairman could report back on what each of their section committee meetings had decided. So that was a shortening of the CCRI meeting itself, but still with the section meetings going ahead. But by the 21st CCRI 2009, when we had a new president, 𝐂𝐻𝐿𝐻𝐿, we expanded a little bit more, had some end users like Carrie Boras here, and I spot Lisa there. Hello, Lisa. And we actually had 3 directors at that stage, not all at the same time, obviously. So past director, Terry Quinn, current director was Andrew Wallard, and the future director was Michael Kuhner. So I thought that was quite an interesting slide to have with 𝐂𝐻𝐿𝐻𝐿 as the president there. And then recently we had the 29th CCRI, and look at this, wonderful. So Dr. Janssen is the president from the CIPM there, and I see, Lisa, you're in front row here. That's nice. So, quick history of department heads. Andre was the first department head, and he was succeeded by Jörg Müller when he retired. And Jörg was a super chap. He really was the most amazing scientist. He did so much work in activity measurements, and his mathematics skills were beyond comparison. But he wasn't really a person people, if you know what I mean. Mireille then took over when George retired, and she was super. Lovely, lovely lady. And she was really responsible for the X-ray work in the department. And she was head for 2 years before she retired. And sadly, this last month, she died. So this is a homage and tribute to Mireille as well. I followed Mireille, and then I was succeeded by Jose Maria Los Arcos from the CMAT, and then Stephen Judge, and now Vincent. So that's a lovely succession, I think. So I've briefly covered from the SEMRI to the CCRI, from neutrons to the Pavillon de Maille, where we are now, but with this wonderful workshop underneath, which we have used, and I'm sure the Bureau is indebted for. And from Andre, raising a glass to you all, to Vincent. And I'd just like to thank you, and particularly my IR team at the time, the BIPM archives, and last but not least, Céline, who has been invaluable in finding some of my archival stuff. So thank you very much for listening.
Thank you, Paula, for your introduction, and thank you to the organizer for inviting us, presenting on the history of the SSDLs. So the IAA has a major role in the SSDL network, so I will set the scene with regard to the IEA. So IAA, the statute was adopted in 1956. And in 1957, it was decided the IAA would have been based in Vienna. It was based in a hotel on the Ringstrasse in Vienna until 1979, and then moved to the headquarters that are currently the headquarters. And this is a picture on the right of the general conference, which was taking place in the Hofburg Palace in the initial years, where now the ball is taking place, the IAA ball. So with regard to the dosimetry in the 90s, in the 60s, so in 1960, a dosimetry laboratory was set up in Seibersdorf. The purpose of the lab was to advance knowledge in radiation dosimetry and to organize dosimetry intercomparisons. And in 1967, the IAA dosimetry section was established in Vienna, but it was still not responsible for the dosimetry lab in Seibersdorf. At the same time, what was happening in radiotherapy? So there was a rapid expansion of radiotherapy, notably in Latin America, and with the use of teletherapy cobalt machines and LDR brachytherapy afterloaders. And there was a shortage of qualified medical physicists, and there was no or limited national calibration capacity, which means that the end users had to rely on overseas laboratories. So there was therefore a need for training of medical physicists, for medical physicists at all, for training of medical physicists, and for accessible and traceable calibrations. So this is where the network was, the idea of the network was then established. And actually, the origin of the establishment of the SSDL network dates back in 1968, where to address the needs that I mentioned in the previous slide, a symposium on the need for dosimetry in radiotherapy centers was organized in Venezuela. And it was jointly organized by the IAA, the WHO, and PAHO. And the panel submitted 3 detailed recommendations to their respective organizations for implementation. First one was to prepare a basic manual of dosimetry. Second one was to organize regional training courses in radiotherapy physics. And third one was to create a regional dosimetry and calibration facilities in South America. Actually, the IAA authorized its dosimetry section to implement the first 2 panel recommendations. So a guideline was published. It's the one showed on the right. It was named the Manual of Dosimetry in Radiotherapy, published in 1970, and some training courses were organized, but the IAA did not approve the third proposal, which was setting up regional dosimetry laboratories, primarily due to financial concerns. But WHO in concert moved to implement the proposal for setting up regional dosimetry laboratories in clinical departments. So WHO convened experts and IAA staff in Geneva to address radiotherapy and radiation protection dosimetry in November 1968, so right after the Venezuela meeting. And the group endorsed Caracas panel recommendation and work on the WHO draft guidelines for the setting up of secondary standards dosimetry laboratories. And the WHO started designating regional dosimetry reference centers within radiotherapy departments under its WHO Collaborating Laboratories program. So the point was that there was no coordination between the IAA and WHO, as you can clearly see, and that the proposal moved forward by WHO had structural limits. So there was limited early communication. Yes, this I mentioned. So limited coordination between WHO and IAA, specifically on regional dosimetry reference centers. The other point is that these centers were embedded in clinical units with limited metrological integration. There was no formal linkage to BIPM or the PSDLs, so neither BIPM nor other PSDLs were officially approached at the time. And there was no structured collaboration among WHO centers, so there was no active linkage support via the existing IAA dosimetry laboratory. So at the same time, in the IAA there was an organizational alignment. And what happened is that in the field of dosimetry, the IAA dosimetry section assumed direct responsibility of the agency dosimetry laboratory, resolving prior inefficiencies and lack of coordination. So there was full utilization of lab manpower and facilities, which enabled a coherent dosimetry program, and a collaboration was established with some national primary standards laboratories. And in that time, a modern concept of SSDLs was developed, which was closely linked to National Standards Lab at the BIPM. So this concept was that the IAA dosimetry lab was designated as a coordinating laboratory for SSDLs, and it was a training center for SSDL personnel, that the postal TLD comparison had to be extended for periodic SSDL quality assurance, and the PSDLs were providing a reference irradiation. It was the need for a formal structure to harmonize SSDL work and ensure access to international measurement system was recognized. And the proposal was to organize a meeting to further discuss the SSDL concept. This meeting took place in 1974. It was again jointly run by the IAA, WHO, and PAHO. The participants were these three international organizations, some PSDLs, the regional dosimetry reference centers, the IOMP, the BIPM, and Euratom. And the recommendations of this panel was to establish an SSDL network with joint IAA-WHO Secretariat, to create an advisory council to guide the Secretariat, and to find the roles and responsibility and quality criteria for membership in the network. So the strategic direction was that a metrology-linked SSDL network was preferred via BIPM and the PSDLs, and the rationale was that PSDLs can maintain primary standards but cannot meet all calibration demands, and expanding radiotherapy, nuclear medicine, industry, and radiation protection applications all require adequate national and regional capacity. So the solution was to establish and sustain SSDLs linked with the PSDLs. So IAA-WHO formed an SSDL task force in the upcoming years, and the task force prepared a document entitled Working Arrangement between IAA and WHO on the establishment of the network of SSDLs. And finally, 1976, the network was formally launched by the DGs of the IAEA and the WHO, who formally announced by circular letters to their member states the establishment of the IAEA-WHO network. So 1976 is the date where the SSDL network was formally launched. And with these announcements, also the preliminary criteria for establishing SSDLs were circulated. And with regard to responsibilities, the WHO had a secretariat for an interim period, and the IAEA had responsibility for technical and scientific development, which is still the case right now. So right after the launch, formal launch, there was a rapid expansion from 8 to 30 members within 15 months. And there were 11 PSDLs who were affiliated to the network and 5 collaborating organizations, the BIPM, ICRU, IEC, OIML, and the IOMP, which are still collaborating organizations to the SSDL network now. So what was also important that within the IAEA, the concept and the support to sustain growth of SSDL was included in the IAEA technical cooperation program, which allows supporting SSDL's development of SSDLs in LMICs. Another important step, which was also addressing recommendation of the panel in Rio, was the establishment of the scientific committee. It's named SSC, and the first meeting took place in 1984, and it's still taking place. So every 2 years, this SSC meeting is taking place, and it's providing a recommendation to the IAEA dosimetry section on the programmatic activities. At the time, it was only for the SSDLs. Now, this committee is providing a recommendation on the all programmatic activities of our section. And as you see, the composition is very important. So the BIPM is there, ICRU is there, one member of one PSDL is there, one member of an SSDL, and then 1-2 other experts are in this panel. So this is how BIPM, ICRU, and the community of PSDLs and SSDL have a very important role in the programmatic activities of the IEA, and where this is all linked, and the nice structure that Vincent showed this morning somehow is also reflected in this committee that it is advising the IEA. So the function of this committee is to advise on intercomparison techniques and methodological consistency, ensure traceability to the BIPM, review SSDL annual reports, and provide technical information and training guidance. As mentioned, the functions now have been extended to the whole programmatic activities of the dosimetry and medical radiation physics section. And the report is then so the committee reports directly to the IAA and the WHO DGs and is published in the SSDL newsletter. So the final report goes up to the two DGs in the two international organizations. So this is how the framework looked like, and still it's the same, just we drafted a little bit different, but it was first published in 1985. And these are the publications that somehow supported the SSDL framework. These are IAA publications. The first one was published in 1985, and in 1999, the first SSDL network charter was published, with the second edition in 2018, and the third one, which is under development and will be published within next year. So now I will talk about the role of the IAEA, the central role, and continuing support the SSDL network. So starting from 1977 onward, the IAEA provided technical assistance through the Technical Assistance TC program, the Technical Cooperation Program, and supported the establishment of many SSDLs, which now form the network. Its assistance has ranged from small projects to large-scale projects in which the agency has provided, over a period of several years, major basic equipment for the use in SSDL and training of staff. So between 1977 and 1997, more than 80 projects in the field of the dosimetry were completed, in 4 member states. And additionally, coordinated research projects covering a wide range of topics related to radiation metrology and quality assurance procedures have been organized with the participation of many SSDLs. Another important step with regard to dosimetry in the IAEA was in 1995. Under the Pedro Andero leadership, the IAEA expanded its mandate from dosimetry to dosimetry and medical radiation physics, and the section was expanded to, so the name from dosimetry to dosimetry and medical radiation physics. So this shift from dosimetry and calibration standard are allowed to include also and expand to clinical medical physics, quality assurance, and implementation. And this allowed a stronger integration of metrology with the clinical practice, quality assurance, and training in all areas of medical physics. And a central role is played by the dosimetry lab, as mentioned. It acts as the network central laboratory. It provides cost-free calibrations for SSDLs and dosimetry comparisons, and dosimetry audits, expert advice to SSDLs, and practical training. And over the years, a continuous service expansion was performed to meet evolving modalities and needs. And I think it's important to highlight that the investments done by the IAA has been pivotal to equitable access to dosimetric traceability, especially for LMICs. So there have been some upgrades over the last 25 years and even before in the dosimetry lab. The irradiation capacity was expanded with new bunkers hosting a cobalt-60 unit, an X-ray machine, a LINAC, and an HDR afterloader. The lab spaces were upgraded for TLD readers, later complemented with OSLDs and RPLDs. And an initiative was launched a few years ago, which is named Renewal Initiative, and it allowed a full refurbishment of the whole Zebersdorf laboratories. Refurbishment or new buildings were created, but with regard to the dosimetry laboratory, it was fully refurbished, and a new training room was created, which is accessible to any time to the dosimetry laboratory for training purposes. These are relevant publications that were published to support SSDLs for the calibration of dosimeters in external beam radiotherapy and recently also for brachytherapy, and other publications. So the SSDL newsletter that is published twice every year, and then guidance on establishing SSDLs and measurement uncertainty, and also on education of radiation metrologists. And notably, next year with ICTP, a new program will be launched to support also radiation metrologists as a postgraduate program. So we have been running this for medical physicists for already 11 batches, and now a similar program will start also for radiation metrologists to give them access to postgraduate education. Nowadays, how does the SSDL network look like? We have 89 laboratories in 77 countries and 16 affiliated primary standards dosimetry laboratories. Since this is some figures just to give you an idea of the impact of the dosimetry lab, since 2010, almost 1,600 certificates, calibration certificates were issued with 8,400 coefficients certified for brachytherapy, general diagnostic, mammography, protection, and therapy. Dosimetry audits. So as mentioned, we run dosimetry audits also for SSDLs and also run dosimetry audits with the support of PSDLs. So since 1967, more than 3,000 beams have been checked in 85 member states. This is a histogram showing the comparisons that the IAA is running supporting CMCs, and also as mentioned, the support to the development of SSDLs through the TC program. Right now we have 42 projects to support SSDLs for their establishment or upgrading of national calibration laboratories or training of SSDL staff, with this diagram showing the distribution among the different RMOs. Knowledge exchange and networking is also important. We organize a technical meeting. Last one was organized in 2023, jointly also with CCRI one. And another important event is the IDOS conference. Next one will be in 2026, which brings together medical physicists and metrologists from the PSDLs and SSDLs and discuss about the dosimetry needs and challenges and updates and achievements. And there is also an online platform with access to important information, and including the DOLNet portal, which is sharing information about capacities of the different SSDLs worldwide. And these are all accessible online, and the publication I showed, they can be downloaded cost-free. So in conclusion, so what the major achievements and the impact of the SSDL network? So the SSDL network was established and now is consolidated globally. It provides direct contribution to the safety and efficacy of radiation medicine for millions of patients worldwide. It contributed to a robust and reliable global traceability chain. And the IAEA audit and comparison programs for the SSDLs have identified and helped correcting systematic errors, leading to tangible improvements in clinical practice. The challenges, sustainability in many countries is an issue, and finding resources to maintain and sustain the labs. The technological gap, it's hard to keep pace with the rapid evolution of radiotherapy and imaging technologies, ensuring SSDLs can calibrate for these complex modalities. The quality system, it's important to encourage the full implementation of comprehensive QMS at all SSDLs. Another issue is the availability, affordability, security of sealed radioactive sources for calibration, and also ensuring the accuracy propagated from the SSDL is correctly implemented in every hospital and clinic. So takeaway message, the SSDLs connect clinical dosimetry and radiation protection measurements to the international metrology system. The SSDL network matured from a regional basis to a truly global and international recognized network. And the continuous improvement through quality management system, audits, training, and alignment to the end users is needed. And I would like to acknowledge Ahmed Mekzifini, who helped in and supported a lot in preparing this presentation, and also has been a great mentor to me, as he was a section head for many years and previously the SSDL officer, and also Zakiti Mzimang, the current SSDL officer, who also is dealing and managing the SSDL network very well, and also supported with the preparation of this presentation. Thank you very much.
So once again, thank you again for the invitation. I'm going to give you a little bit of a history and background for the ICRM. First of all, who are we? We are a group of member institutions that are engaged in research regarding the measurement of radioactivity. We currently have 47 member institutions, the majority of which are national metrology institutes or designated institutes. But we also have a number of universities, non-governmental. Important to keep in mind that the membership of ICRM is the institutions themselves, and not necessarily individuals, although we do have a classification of membership known as associate members. We have about 40 of those, and they don't have a vote in the business of ICRM. But these are typically individuals with specific expertise or experience that contributes to the field, and these are typically distinguished retirees and people who have contributed over the years to a number of ICRM activities. And they also include all of the working group coordinators that help coordinate a lot of the activities within ICRM. The members, member institutions, are represented by delegates that are formally appointed by their institutions. And membership to ICRM does have a formal process, but it is a fairly simple process. The main requirements are that the institutions are actively engaged in research related to the field of radionuclide metrology and applications. So what do? We provide a technical forum for the exchange of information related to the field of radionuclide metrology. And we also provide a forum for forming collaborations between member institutions. We try to promote good radioactivity measurement practice, generally within the wider scientific community. And actually, as part of our founding, we've had as one of our main goals to grow the field of radionuclide metrology for future generations and ensure that that we have a future generation of metrologists that can keep doing the fine work that that the metrology community has been doing for over 75 years. So a couple of the ways that we accomplish these goals, for those of you that are familiar already with ICRM, you probably have heard of us through our main conference. And this is a fairly large conference, anywhere between 150 to 200 radionuclide metrologists coming together almost every 2 years since 1977. There's been a couple of gaps. Most recently, the 2021 meeting had to be canceled because of COVID. But almost every 2 years since 1977, we've had the general conference. Our most recent one was held very successfully here, well, there in Paris, the LNHB. Most of the activities, however, that are done for ICRM or through ICRM are conducted through the 7 working groups that we have. Most of the working groups have interim meetings between the main conferences, and they offer opportunities for in-depth discussions. These are a much less formal environment. It provides more training opportunities, more in-depth discussions. And more importantly, while the main conference tends to be a forum for presenting final results and ends of projects, the meetings of the working groups provide an opportunity to discuss works in progress, and more importantly, to discuss things that aren't working very well and to consult with experts in the field to try to resolve individual problems that you're having in the laboratories. Some of these meetings are fairly small. Like you can see the most recent meetings of the liquid scintillation counting and life science provides a very focused work on specific topics and to concentrate on particular field. But some of the meetings can also be very large, as evidenced by the low-level radionuclide metrology meeting that was held in Gran Sasso in 2022. So a little bit of the history. How did we get here? It's been the origin story for ICRM that it became, it was an offshoot of the 1972 International Summer School on radionuclide metrology that was held in Herceg-Novi in former Yugoslavia. The idea behind the summer school was a realization that we have a generation of radionuclide metrology practitioners that are starting to get fairly long in the tooth, and it's time that we need to pass that information on to the next generation. And how can we do that? So in 1972, this summer school was put together. A large number of lecturers from the National Metrology Institutes and some national laboratories. And the whole idea was to train people on basically the state of the art in radionuclide metrology and learn about the different techniques. More importantly, it was an opportunity back then for the scientists in the East and the West to have an exchange of ideas. This was very difficult at the time, and it was seen as a very good opportunity, particularly for the younger scientists, to meet their counterparts in the West, and likewise the practitioners in the West to find out what's going on in the East, to exchange information. So most of this founding, the founding stories is based very heavily on meeting minutes and correspondence. I'm very lucky to have inherited the notes from my predecessors, Robin Hutchinson and Wilfred Mann, who were copious and meticulous note takers, and they kept everything. So I was able to go through and actually see some of the initial correspondence between the founders of ICRM to find out what was sort of going through their minds at the time. And some of this early history is based on their notes. So in 1974, there was a meeting of the organizers of the Herceg-Novi summer school, but with a slightly enlarged participation group. And the question came up, and this was actually a quote in the meeting minutes from that meeting. So, should not a permanent collaboration be established in other fields than the organization of meetings? And the response to that was overwhelmingly positive. There was a preliminary terms of reference that was drafted, but at that 1974 meeting, there was no representation from either NPL or NBS at the time, and so it was thought that it would be important to get their opinions on these terms. The initial efforts to define the scope were actually quite difficult because there was already the thought that, well, maybe a lot of this work could be done through the BIPM consultative committees. And in fact, there was even one very prominent person in the field from a large international organization, not the BIPM, that noticed this and said, well, I'm not sure that we really need a new organization, since the consulting committees are doing a lot of that work already. But I think that the discussions that followed sort of identified a gap in the remit for the BIPM and the consulting committees, and there was an identified need for more of a, let's say, basic metrology and technical development, a forum for needing to exchange information and develop that field. So in 1975, the quote second meeting of the BIPM, or the ICRM was held, and this was held in Saclay. And at the time, there were 16 member organizations. I can note that the BIPM was initially not a member of the ICRM, but they have Wilfred Mann to thank for proposing their membership. And that was widely accepted at the next meeting. The first set of officers for the ICRM was chaired, and in fact, the idea for a lot of the ICRM and a lot of the grounding work for the foundation was done by Boris Grinberg at the predecessor for LNHB. And the other officers from NBS and NPL and from OMH in Hungary. And interestingly, the executive officer, which is now the Office of Secretary within ICRM, was an appointed position that was essentially some of the secretarial and administrative personnel from whatever the institution from which the chair came. So this was a person that was generally appointed by the chair to assist them in preparing minutes and doing correspondence. So in the founding of the initial ICRM, there was a set of working groups that were set up in the areas of non-neutron nuclear data, development of nuclear energy, alpha, beta, and gamma spectrometry, all lumped together, low-level measurement techniques, and the life sciences. And at that meeting was proposed to hold another symposium on radionuclide metrology, either in 1976 or 1977. And at that time, there was actually a set of bylaws that were drafted that form the basis for the bylaws of ICRM today. So the initial conferences that were held under the auspices of ICRM, things were done a little bit differently then. So most of the activities, if not all of them, were organized by the working groups. General meetings were usually one day, and they were held separately from these conferences. And looking back in the records and the archives of ICRM, the numbering of the conferences is fairly uncertain until 1991 in terms of what was considered the first, quote, ICRM conference. But going back, you can see some of the topics that were addressed. These were either standalone seminars or standalone sessions that were held either as a standalone meeting or in conjunction with larger organizations, such as the American Nuclear Society or other organizations. So early on, the most active working group was the low-level or environmental radioactivity working group, and that actually stands to this day. And in fact, the low-level radionuclide metrology techniques working group organized its own conference that is held, I think, every 3 to 4 years outside of the general conference, and has attendance that is almost as large as the general meetings. But looking back in the archives, 1977, this conference on the development of naturally contaminated radioactivity standards that was held in Woods Hole is generally considered to be the first, quote, ICRM conference. But it wasn't until 1979 that the general meetings and the symposia that were organized under the auspices of ICRM were actually combined. Again, more conferences specifically on general topics or specific topics, either in low-level techniques, life sciences, nuclear data. I could mention in 1985, it was decided that the initial working group on nuclear energy was disbanded, and the view was that the activities of that working group could be handled by some of the other working groups that could be set up. So looking back into the records, I can also say that the 1989 meeting that was held in Braunschweig was actually a combination of multiple symposia run by the working groups, and seemed to be one of the larger groups of meetings. And so this actually became the start of the naming convention with the ICRM in the year. So the ICRM 1989 meeting was actually the first one that started the naming convention that we use today. So as I mentioned before, the conferences are now held about every 2 years. We try to keep it every 2 years. Again, in 2021, unfortunately, the conference was canceled because of the COVID pandemic. But the conferences are hosted every 2 years by one of the member institutions, and we've tried to keep it so that 1 out of every 3 or one out of every 4 of the conferences is held outside of Europe. Even though the majority of the member institutions come from within Europe, there's a growing trend for more institutions coming from outside of Europe. And so, as I mentioned, the 2025 meeting was our most recent meeting held in Paris. And I'm happy to say that our colleagues in Brazil have offered to host the 2027 meeting. And this was accepted by the membership of ICRM, and we're looking forward to meeting down in Rio. So looking at ICRM today, again, we're 47 institutions, 7 working groups covering topics of beta particle spectrometry, gamma ray spectrometry, liquid scintillation counting, low-level radionuclide metrology, which also includes mass spectrometry, life sciences, nuclear decay data, and a larger radionuclide metrology techniques working group that has 3 subgroups dealing with digital coincidence counting, internal gas counting, and large area sources. We have 2 working groups that have been proposed at the last ICRM meeting, and these deal with the development of cryogenic detectors and source preparation. And these working groups will develop a working plan and be formally incorporated into ICRM at the next meeting in 2027. The current list of officers, I'm happy to say that as of last week, the presidency was formally handed over to my friend and colleague Raphael 𝐏𝐫𝐬𝐬, sitting in front of you. And we have a slate of vice presidents from national metrology institutes in Germany, the UK, and France. Our secretary, Frida van Weingart from ANSTO, and I recently became the past president. So the future of ICRM, we have this discussion quite a bit to see where are we going as we move into the future. We've been around for over 50 years now, and one would think that after all of this time that everything's been said and done, and that there isn't a lot of development in radionuclide metrology, but you'd be wrong. There's a lot of new detectors that are being developed. The advent of AI and machine learning and how that can get incorporated into radionuclide metrology, and of course, the development of Monte Carlo techniques. There's also new spectroscopic analysis methods and a lot of other source preparation techniques that are under development. And there's a need for dissemination of information and training in these methods. Again, as part of the founding of ICRM, it's always been important that the transfer of knowledge and training the next generation is an important aspect of ICRM. And this becomes increasingly important as university programs disappear. People generally don't come into national metrology institutes with the background and the training that's going to prepare them specifically for the jobs that they're going to be doing as metrologists. And so it's important for the NMIs and for organizations such as ICRM to help with that knowledge transfer from one generation to the other. The encouragement of metrology as a profession is also a relatively new topic that's been taken up by ICRM, and we're looking forward to actually having our first Young Scientist Award starting with the ICRM 2027 meeting. We've also opened up to other communities that typically wouldn't be part of the radionuclide metrology community. The low-level radionuclide metrology techniques meeting that was held in Gran Sasso presented a great opportunity for interactions with the high energy physics community that we haven't had before. and we saw an uptake in some of the interest in our activities and a growing list of collaborations that was evidenced by some presentations at the following main meeting in Paris, dealing with high energy physics and some of the problems that are associated with that particular field, and of course also broadening aspects of radiation measurement, and of course a new interest in non-proliferation and nuclear security. So I would encourage everybody to get involved if you're not already involved with ICRM. ICRM activities are open to everybody, not necessarily just for the member institutions. So our working group meetings and our conferences are open to everybody, and we encourage you to participate. We do have a new website, and that's given here. And it's also what will come up if you do search for ICRM and radionuclide metrology. Just to highlight a couple of upcoming events, we have working group meetings for the liquid scintillation counting and life sciences working groups that will be held in June in 2026 in Ottawa, as well as the low-level radionuclide metrology techniques conference that will be held in September of 2026 in Ottawa. As I mentioned before, the ICRM 2027 meeting is tentatively scheduled right now for the 17th to 21st of May 2027 in Rio de Janeiro, and please be on the lookout for those announcements in the future. So with that, I'll thank you for your attention, and I'll be happy to take any questions.
Just before lunchtime, I will not be long. I just would like to have a special session as an homage to all those who has worked at the BIPM IR department. But I would like first to start with a few words for people who have disappeared these last 2 years. So maybe I've forgotten people. So I will just focus on 4 of them. So first we have Jose Maria, which was head of the department before Stephen, and who unfortunately died two years ago. And so just to have some memory of who he was, what he has done. We mentioned Mireille Boutillon, which was already introduced. It was I did not know her at all, but all I heard about her was fantastic. So it was a very nice person, and she just passed away 1 month ago. For the CCRI part, we had Tony Albert, which was someone of importance. I don't know him, but people from Section 1 know him, and he was highly involved, I would say, in the early 2000 part of the CCRI, and recently also Horst Klein, which was important figure of neutron metrology from PTB, was also some. I just want that, at least for those who know all this person, have a few seconds of thinking about them. So to move to another part, just would like to have all these people here have been worked as a BIPM staff, as BIPM staff department. So this is all those who are not here. So André Allisy, of course, which was the founder, and if we have BIPM IR department is existing, is mostly his work. So just. And I just would like to invite all the BIPM staff of yesterday and of today to come in the front of the screen. I would like to take a picture with people from the past virtually and people for today. So please come in, my dear colleague, and I would like that you have in mind that all these people that you are seeing on the picture and that we have in front of you are working for you.
Good afternoon, everyone. Thank you to the organizers for having invited me to give this talk. So as the chair, thank you for the introduction, said, I will speak for this first talk regarding the use of ionizing radiation for health. My position currently is at the French Authority for Nuclear Safety and Radiation Protection, but today I will speak with my ICRP hat. So just maybe for those of you who are not so familiar with ICRP, I will give a short introduction for what ICRP is, just a very quick overview. ICRP is the International Commission on Radiological Protection. It's an independent organization, a charity gathering more than 300 experts all over the world, and which has been established almost 100 years ago. The mission of ICRP is the advance for the public benefits, the science of radiological protection, by providing recommendation and guidance on all aspects regarding ionizing radiation. So for that, we have the general recommendations, which are updated regularly, but not very frequently. We are currently updating the last publication of the general recommendations. And together with this general recommendation, we have a whole bunch of publications on very dedicated to specific topics like veterinary use or brachytherapy or deep geological disposals. And for that, we have a main commission and 4 committees. One of these 4 committees is on medicine, and task groups were really those who work to prepare the publications, and a few working parties. So it was just for the introduction of ICRP when I move to the topic of the talk today. And so the use of ionizing radiation in medicine. So first, I will give a very quick overview of what for ionizing radiation are used in medicine. Why do we care about radiation protection in medicine? The principles guiding radiation protection in medicine, and also the needs we have regarding optimization. So what are the use of ionizing radiations in medicine? So you have an overview here. I think you all have an idea of how we can use ionizing radiation in this field. So I will just go a little bit more in details regarding this use. The first main area of use of ionizing radiation in medicine is diagnostic, gathering the use for mammography screening, dentistry, conventional radiology, computed tomography, and also the diagnostic part of nuclear medicine. So it's a mix of both external exposure and internal exposure. The second broad category of use of ionizing radiation in medicine is to guide a surgical operation. So it's what we call interventional radiology. For instance, for coronary arterioangioplasty or embolization of AVM or vertebroplasty, for instance. So it's still use of X-rays, rather low energy, but for long procedures, so the level of doses can be higher than, is higher than the conventional radiology. And the third main category of use of ionizing radiation in medicine is for therapy. Here you have 3 different categories of therapies. The external beam radiotherapy, mainly the main use for cancer treatment, or brachytherapy, and also nuclear medicine therapy, so the therapy part of nuclear medicine. So these are the 3 main areas where we use ionizing radiation in medicine. So why do we care about radiation protection in medicine? Actually, according to the last UNSCARE report, we have the estimation of about more than 4 billion examinations per year worldwide, more than 1 million radionuclide treatments, and more than 6 million courses of radiation therapy. In France, the medical exposure are responsible for more than 20% of the global exposure, the mean global exposure of the population. All sources included. But just a warning, this part in blue, the 20%, 23% is only for diagnostic procedures. It's not for therapy. They are excluded, otherwise we will have blue all over the cycle. And medical exposure is the largest contributor to radiation exposure to the population from artificial sources. So that's why we need to have an eye on the radiation protection of mainly patients, but also the workers in medicine. So the principles guiding radiation protection in medicine for patients here are defined in the reference publication by ICRP, which has been issued some years ago, which is a publication 105, Radiological Protection in Medicine. And these two principles are justification and optimization. Justification means that the benefits of using ionizing radiation on a patient should be superior to the risks of using the ionizing radiation. And optimization is the second principle, which is a little bit different if we speak about diagnostic or therapy. For diagnostic, optimization of the dose means that we should deliver to the patient the lowest dose for the proper diagnostic purpose. So we need the lowest dose as possible, but we still need to have the good quality of image to be able to give the proper diagnostic. For therapy, the optimization principle is a bit different. The goal is to deliver the highest dose as possible in the target volume, I mean the tumor cells, while preserving the neighboring organs, not to create more complication than the initial sickness. So for optimization, to apply this principle, the hospitals need for several tools. First, the need for the proper international protocols, mainly developed by the IAEA. They are the reference document for medical physicists in the field. They need also dose measurement tools provided by manufacturers, calibration of these tools, which is performed by the national laboratories, and those audits. And all this in the context of significant technological developments in diagnostics and for the preparation and delivery of the treatments. Here you just have a schematic representation of all the evolutions we had these last years in radiation therapy, for instance. So you see that from these 25 last years, we had a lot of developments, technological developments, with an increasing complexity in the way that treatments are delivered. Plus, of course, like in all other fields, the development of the use of AI-based tools, which is also another difficulty. So now the second part of this talk, after having presented the use of ionizing radiation in medicine, is regarding the needs for metrology in medicine. So the topic of the talk was the needs for the future, but actually they are already there. So I will again split this in three parts. The first one for radiology, so imaging, but only radiology, nuclear medicine, both diagnostic and therapy, and radiotherapy. For metrology and imaging, so for radiology, regarding dose optimization, metrology enables the measurement of patient exposure to radiation through dose indices and supporting imaging protocols that balance diagnostic quality with radiation safety. So again, this is the principle of optimization. Regarding quality assurance, there is a need for regular calibration of the dosimeters which are used for the optimization purposes, and the verification of imaging devices to ensure the consistency and reliability of each device, but also among devices across institutions, for instance, for clinical trials, supporting early and accurate diagnosis of possible deviations on dose or on image quality. So, for instance, one example of innovation here, you have a kind of device used in the operating theater. And as new imaging techniques are more and more used, and particularly in interventional radiology, metrology must evolve to provide the proper standards and measurement methods for these novel technologies and also calibrated dosimetry equipment. For that, in Europe, there is currently an ongoing project, which is TRAMEXI. Some of you know it very well. It's a TRAMEXI for traceability in medical X-ray imaging dosimetry. And on the left part of my slide, I put a quote of what is written on the website. And it says that the procedures used by calibration laboratories currently do not fully consider the recent technological developments in X-ray imaging. So there is a need for updated measurement and calibration procedures that will be proposed by this project for inclusion into standards and protocols. Now, if I move to nuclear medicine, here again, but I think you had the specific workshop yesterday for that. Sorry if I say something that you have already heard yesterday. There is a need for accurate calibration of activity meters and calibrators to ensure that patient receives intended diagnostic or therapeutic activity. And there is a need also to ensure the relevance of data for comparisons between different centers and studies, again, for instance, during research or studies or clinical trials. Again, in Europe, there is an ongoing project which is named eTrain, which goal is to create traceability infrastructures for nuclear medicine and to harmonize nuclear medicine measurement across Europe. And now I would like just to make focus on the hot topic, let's say, of the that we have currently for therapy in nuclear medicine. It's alpha therapies. This is something which is gaining more and more in importance. At the last EANM meeting, the European Congress of Nuclear Medicine, it was a number of sessions regarding this topic. The targeted alpha therapy, which is developing a therapy currently in nuclear medicine, as you can see in the table on the left, on the right, sorry, of the slide. There are a number of clinical trials ongoing regarding this particular kind of therapy in nuclear medicine, which use mainly actinium-225 or lead-212. And it's a novel targeted cancer therapy, mainly for neuroendocrine tumors and metastatic prostate cancers. So it's very something which is gaining in importance currently. Again, for that, there is a European ongoing work, which is called AlphaMet, for the metrology for emerging targeted alpha therapies. And the aim of this project is to generate metrological network for safe therapy in alpha therapies, targeted alpha therapies, sorry. And the aim of this project also is the development of primary and secondary radioactivity standards for alpha emitters. There is also an ongoing work by the IEC with a specific committee in charge of the development of protocols for calibration and quality control in the use of radionuclide calibrators. And there are so many others that could be cited. But if you are interested in this particular topic, I can advise you to have a look to this paper published by Zimmerman and colleagues last year. Well, at the beginning of this year, of gathering the summary of a workshop which has been organized on the needs for radionuclide metrology in the use of alpha emitters, and it is a very good paper. In this paper, again, I quoted on the right a sentence that seems important for me. The improvements in radioactivity measurement for alpha-emitting radiopharmaceuticals during preclinical development are crucial to the successful implementation of new treatment candidates before clinical acceptance. Because we need to know which kind of activity precisely we deliver to the patient. Dose is something else, but at least activity, which is delivered to the patient to be able to compare the results and the effects on the patients. So the use of new radionuclides, especially alpha emitters for targeted therapy, presents challenges in measurement and standardization that metrology should address to enable the safe clinical adoption of this kind of therapy. And I think we will have a specific talk in some minutes this afternoon on that. And last slide regarding radiotherapy. Here, the doses that are delivered are much higher with the beams of very high intensity. So again, we need primary standards and traceability. National and international standards for absorbed dose are needed to contribute to ensure that the prescribed dose match the delivered dose. And regarding innovations, which have started recently or are still ongoing, we have the rise of techniques like MR-Linacs. Well, for these ones, they are already used in clinics, and we can more or less think that the issue is solved. But we have also the development of spatially fractionated radiation therapy, flash therapy, which is a big topic, and BNCT, boron neutron capture therapy, which they all require new measurement protocols and standards to address the complex dose distribution, high dose rates, and also sometimes a combination with very small fields. So in my last slide, I will develop only flash therapy and BNCT for the time. Flash therapy, maybe some of you know already, so sorry if I say something you already know. Flash therapy is actually the combination of an ultra-high dose rate beam, much higher than the conventional dose rate that we currently use in conventional radiation therapy. And it is expected while using these UHDR beams to have the generation of a radiological effect that we call the flash effect. And so what is the flash effect actually? Is that under certain circumstances, we can have the effect that for the same tumor control, we have less complication for the surrounding healthy tissues. So we can expect to be able to deliver more doses in the target volume with the same side effect for the patient, or to deliver the same dose in the target volume, but with lower side effects for the patient. So these are the expected benefits, but only a word of caution here, because to date, the parameters to obtain the flash effect and the possible long-term risks are not well mastered or known. It is a very active domain of research on plenty of parameters, because this flash effect can be obtained with electron beams, with photon beams, with proton. So you can imagine the number of experiments you can do. It's depending on the kind of tissue which is irradiated. It depends on the volume of the beam, or the target irradiated. It depends on the number of pulse, on the intensity of the beam. Well, it's so many parameters to be considered. So it's a very complex topic. So for metrology, there are, of course, challenges for flash therapy due to these very high dose rates and the pulse structure of the beam. So it makes the consequence are that the direct application of dosimetry protocols designed for conventional radiation therapy is currently impossible without additional consideration. And it is essential that national metrology institutes provide adequate traceability routes for flash therapy to ensure that we can implement it in a safe manner. And these two dots are just conclusion of a very good topical review, which has been published by the team of Anna Subil last year. It was a conclusion of the UHD Pulse project under the Empire umbrella. This project ended 2 years ago, but now a new one is started, which is the flash dose for traceability dosimetry for flash radiation therapy. It has started in June this year under the umbrella of Euramet. And there is also the AAPM, so the American Association of Physicists in Medicine, who is working on this topic under task group 359. So they are also trying to develop a guidance for flash radiation dosimetry. So let's hope we have answers rather soon on this topic. And two last slides. I hope that I'm not too long. I don't know exactly how long I took until now. Tell me if I'm too long. BNCT. So what is BNCT? It's boron neutron capture therapy. It's an interaction between a neutron beam and boron-10 particles, which are injected in the patient before the exposure to a neutron beam. And the interaction between neutron and boron produce alpha particles and lithium particles, which have the particularity to deposit the high energies, a lot of energy, rather close to the cells which are irradiated. So it is something interesting for the treatment of cancer also. And Japan is the first country where BNCT has been approved and is covered as cancer therapy by the public healthcare system. If I speak for France, we are very, very far from that. We even don't have one installation for BNCT in France, and I don't see any plan for that in the next month or years. So I don't know what will be the future of this therapy. I know there is one in Finland and some other countries, but Japan is the first to have it covered by the public health system. And the challenge in BNCT is that absorbed dose concept of conventional radiotherapy cannot be applied because of the very different dose components with very different biological effects, which are produced during the interaction, which are the basis of a lot of differences compared to a conventional photon or electron therapy. But also on that, there is an ongoing work by the ICRU with the report committee 39, prescribing, recording, and reporting for BNCT. And I don't know what is the status really of this paper, if it's close to the end or not, but there is this ongoing work regarding BNCT. So last slide, as a conclusion. Ionizing radiation metrology is foundational to the safety, efficacy, and advancement of medical application involving ionizing radiation. Its role gains in importance as medical technologies become more precise, complex, and patient-centered. There are several studies on metrology all over the world that are underway to try to bridge the gaps between the treatment or diagnostic techniques that are in development and the need for accurate and traceable metrology for the safety of patients. Thank you.
All the same. So good afternoon, everybody. Apologies firstly that this meeting's, my presentation's online due to other commitments. I was unable to attend, but one of my team, Wilhelm Röntgen, is present. So let me start by saying good afternoon. I'm John Burnett. I'm the laboratory head of one of the IEA laboratories, terrestrial environmental radiochemistry laboratory based in Seibersdorf in Austria. And as you can see from the slides, my presentations on ionizing radiation in the environment and meteorological needs. And I thought it'd be interesting to present the needs as my laboratory sees it in its mission to help member states with their measurement of ionizing radiation in the environment. So broadly speaking, a quick bit about who we are, just to set the scene. Our job is to help member states to measure ionizing radiation in the environment. So natural radioactivity, anthropogenic radioactivity, anthropogenic sources, of course, fission products, activation products from nuclear power plants, weapons testing, medical procedures, mining activities, for example, natural sources as well, predominantly from uranium-238, thorium-232 series, and potassium-40. A significant emphasis as well on helping prepare should there be an accident, some sort of unintentional release into the environment that could occur. And we do this through four main capacity building activities, two of which we'll expand in a bit more detail in this presentation. This includes proficiency testing, provision of reference materials. We provide dedicated expertise and trainings, and we also provide laboratory analysis. So, as I mentioned, we'll talk more about proficiency testing, reference materials in a moment. Expertise and trainings, we're undertaking a lot of trainings. We good? So I had a question. Okay. So expertise and trainings, we provide a lot of trainings both in Austria and Vienna. And we also do regional trainings, online trainings. We produce a lot of technical documentation, including the technical report series, as mentioned in the previous presentation. We produce these for radionuclides in the environment. Recently, we've just released one on tritium in the environment, for example. Number of trainings, as I mentioned as well. Laboratory analysis, we do this in two main areas. We perform confirmatory analysis, where samples can be sent to my laboratory to confirm the measurements being made by a member state. A good example being for the water. Okay, I'll continue. A good example being I'm hearing someone speaking. Is everything okay?
I'm sorry, please shut down your microphone. Yeah, but it's
I think we're good. Okay, if that was a question, I'm not sure. So we perform a laboratory analysis. This can be confirmatory measurements. For example, waters that are cleaned up from the Fukushima facility. These get sent to my laboratory plus the IEA laboratory and the isotope control. I think we're having a few conversations running in tandem. You good?
It's coming back in again. Yeah, I would put it out. Supprimer. Okay.
Apologies to the participant who got kicked out. Okay, back to where I was. So laboratory analysis, we do this for two main reasons. Confirmatory measurements. So a member state can request that the laboratory helps confirm the measurements that are being performed. A good example is we perform confirmatory measurements on the out-treated waters from the Fukushima reactor. These get sent to this laboratory plus the two other IEA laboratories at Monaco and the Isotope Metrology Laboratory. We confirm the measurements and we share those results transparently with the international community. The second instance is if a member state doesn't have the capability themselves. A good example is more sensitive techniques, ICP mass spec as an example. Samples can be sent to us to perform the measurements on their behalf. But those four main ways, so proficiency testing, reference materials, expertise and trainings, and laboratory analysis, are the ways we help member states to measure ionizing radiation, radionuclides in the environment. So the main area just to look at first and to share our experience it on what the requirements are as reference materials, because it's one of the main ways we help with the metrological requirements. We all know what reference materials are. They're fundamentally important for quality assurance purposes. The Turk laboratory, we have ISO 17034 accreditation since 2022, and we supply just under 2,000 reference materials a year to between about 70 to 80 different member states. We supply radionuclides in reference materials, a wide range of materials. We also supply stable isotopes, organic contaminants and trace metals. For the stable isotopes, we hold the primary reference materials, the carbon, hydrogen, oxygen, nitrogen, sulfur isotopes as well. We provide these, are available on our website. To mention, we're not for profit. We have a nominal fee, a few €100. We waive that if budgetary resources aren't available for a member state. But this is one of our key activities, and assessing how we can help in this area is quite important. So we'll look at this in a bit more detail. So as I said, we supply all over the world. Last year, it was 1,899 units to 59 member states. And we supply a wide variety of different materials as per our mission. So we have two kind of broad categories. We have materials that fall under our ISO 17034 accreditation, and those that do not. For the ISO 17034 accreditation, we have 7 different materials at the moment. It includes in itself a wide range of different types, as reflected by the requests from member states, from rice to sediments to soils, milk powder, for example, fish, seawater, and more recently, the mining waste. Then we have on the right-hand side, we can see the non-17034 materials. These can be divided into CRMs, so certified reference materials, and normal standard reference materials. And again, we have a wide range of sediments, foodstuffs, chemicals even, and even at the top, it's quite interesting, we have material from 𝐏𝐫𝐸𝐿. I'm sure many of you are familiar with the French nuclear tests. Ended in 1996 at 𝐏𝐫𝐸𝐿 and Mesures. Well, this laboratory and the other IA laboratories were involved in the environmental impact assessment, resulted in a quite groundbreaking report in 1998 on what the environmental radiological conditions were in the area. As part of that, we collected a lot of material, and a reference material was also produced. But these 17 different reference materials that we have available right now break down into the categories soil, sediments, foodstuffs, seawaters, mining waste, vegetations, and chemicals. And we have quite a large remit. Our job is to help. How do we prioritize this help, and how do we decide what materials to produce? Given, as I'm sure all of us appreciate, to produce reference materials is quite a lot of work. It takes between 1 to 3 years at best. In some instances, quite longer. It takes a lot of resources as well. So I thought this would be quite interesting, assessing the meteorological needs of member states. Well, what did member states say? Because we actually undertook a survey in 2024, and we asked 865 participants from both our reference material sales and our proficiency testing programs on what their thoughts were, because this helps guide what we do to help member states. What do we focus our finite resources on in terms of what to develop? I thought this might be quite an interesting area to look at for the purposes of this workshop. So main areas of interest from the participants on what did they use these reference materials for example. Let's see, the main areas were for calibration purposes, in support for quality systems, such as ISO 17025, method development activities, research activities, and for services as well. And then we asked, what are the most important types? And we can see on the right, soils and sediments are amongst the most important. Fresh waters was highlighted, vegetation, foodstuffs, marine waters, like seawater, for example, construction materials, mining waste, and even gases. Now, this was quite important. For our lab, we don't actually have an offering right now for fresh waters. We do in the other areas, with the exception of gases, and this has helped target that we're going to produce a freshwater material starting early next year. And Ivana, who's in the audience right now, is part of that program. What was important was the need for these reference materials to be accredited as well, so to ISO 17034 was identified as being important by 91% of participants. So for our laboratory, which is obviously embarked on this accreditation process, it's quite reassuring to know that adds value to the materials we provide to member states. So we asked in another question, what were the materials, the matrices that were being requested? The ones in red are the ones we currently have available, similar to what we saw on the other slides. Freshwater was also requested, concretes and air filters were also asked as new areas. They're in yellow because we're able to address it. We're working on this area in the next year and the year after. Green areas are ones which we're not currently involved in at the moment. We'll look at these yellow ones in a bit more detail in just a moment as well. It includes some quite interesting areas as well. Concrete, we've had a number of requests and we're looking at some feasibility studies on developing a concrete material. It's of value for decommissioning purposes. Air filters, some of our team are working on quite a novel approach to print, basically radioactivity. We already do this on simulated swipe samples. And for calibration of probes, we can basically use radioactive ink to print a sample. We'll aim to expand this technology to produce a printed reference material in the near future in this area as well, again to meet the needs of member states. For these growing requirements, we had to change or expand, actually adjust our 17034 scope this year as well. It was quite restrictive. Previously, it was on specific matrices and radionuclides, which doesn't enable us to flexibly produce materials to meet the growing requirements of member states as per our mission. So this was expanded, and this is quite a wordy slide, so please don't try and read it all, but allow me to summarize into two main categories of reference materials. That's environmentally originated materials, so things like water, soil, sediments, seawater, that sort of thing. And then anthropogenically processed natural and artificial materials. So mining waste that's been gone through some processing, for example. Building materials, they originate from natural materials, but they've obviously been modified slightly, or fabricated materials. And it enables us to produce them through three main ways. So we can use materials that are already contain some level of contamination or radioactivity in them, so like legacy contamination, soils from Chernobyl, for example, or Fukushima. We can add radioactivity by formulation, where we spike things, spike cesium, for example, into foodstuffs, milk powder, or other soils, as an example, strontium. Or we can combine the two. So we can use intrinsic contamination and add it by formulation to produce kind of a hybrid approach. But this is our kind of methodology to be able to produce a wider range of materials that we're now embarking on to help meet growing requirements. Some examples of recent materials: milk powder, is a spiked milk powder produced by formulation, containing cesium, barium, and strontium, for example. Soil, this was the combined approach. There's natural radioactivity, for instance, potassium 40, and then it's spiked as well, barium, cobalt, and radium, for example. One of our new materials, and again, Ivana in the audience has led much of this work, is this new mining waste. This is again to meet emerging requirements from member states to produce a wider range of materials. This was quite an interesting material that we've literally just released now, and is also published as well in Applied Radiation Isotopes. This was kindly supplied by IEA Collaborating Centre, the Radioanalytical Reference Laboratory, RL, in Hungary. And this is a key area where, and a key kind of factor in the production of our materials, we have a lot of needs to meet, and help from others is massively appreciated. And RRL has been a fantastic collaborator. They provided this material. It was from mining waste from an aluminium mine. It contains a lot of natural radioactivity in relatively higher levels, making deconvolution quite difficult via chemical spectroscopy. It's also slightly higher density. It even contains a small amount of legacy contamination, cesium-137, from the Chernobyl accident in 1986. So it's a nice new material that we've just produced and is available to member states. Last year as well, another material we produced was our IEA 482, which is a fish material, again, kindly provided by another IEA collaborating centre, the Korean Institute of Nuclear Safety Akins, in the Republic of Korea. This is basically a dried anchovy that contains some natural radioactivity and was spiked as well. And our colleagues in Hungary, the Radiological Reference Laboratory, again helped with some of the processing. The rest of the measurements performed by our laboratory is also available. And again, meeting these growing kind of needs and requirements, we've been able to try and produce a wide range of different materials. You know, we're only a small laboratory of 22, 23 people. This year, or starting in 2026, really, we're beginning a new 17034 certified reference material on barley, and this is quite an exciting material. It expands the growing need for foodstuffs, because right now we have some limited offerings. We have a rice material, but we do need another food material, and barley is a very good one. That's been very kindly produced by the Allisy State Radiation and Ecological Reserve of the Republic of Belarus in the Chernobyl exclusion zone. It contains a lot of legacy contamination. That's currently being transported to our laboratory right now, and we'll begin characterization work on it in the new year with an anticipated release date of Q1 2027. We also have a water that's under development. Again, you saw the request from member states for a freshwater material, and this will begin characterization shortly. This will also be combined with an expansion of our ISO 17034 scope to include actinides. Right now it's based on chemical spectroscopy. It will be expanded to include the actinide side of the house as well. So uranium, for instance, will be characterized in this material. And we have a reissue of a previous reference material as a ISO 17034 material, a stream sediment that will be released in Q2 2026. Then other materials just on the horizon. Again, it shows a wide variety of materials that member states are requesting. Our lab, we have a diluted uranium ore. This has been in the works for a few years. Looking at the data quite closely, and there's been a few things we've had to check and so on. This should hopefully be finished next year as well. And also a bamboo material, which has trace amounts of radionuclides from Fukushima accident. The printed materials, this is a novel area of our reference material activities and our proficiency test work. As I mentioned, we've developed a technique that enables us to print radioactivity. In one instance, we used specially modified inkjet printers with radioactive ink. We carefully control the chemistry so it stays stable, and we're able to produce a wide range of printed radioactive sources. We see some smaller square sources on the right, and then larger A4 size printed sources for calibration purposes of in situ chemical spectroscopy equipment. This in itself will be looking to produce air filters, as I mentioned, for reference materials, but very interestingly as well, we're looking at applications to develop 3D printed materials as well. So our plan right now is in the timescale of approximately maybe 2 years, we'll aim to have a filament, radioactive reference material filament that will be available for 3D printed purposes. And there'll be lots of applications to validate gamma spectroscopy calibrations, for example, or even density matched calibrations. You could even imagine down the road printed phantoms, which are density matched and anatomically correct. The radioactivity is in the correct places, bronchial structures of the lungs, for example, to help to improve on the calibration. Or animals. We're printing skeletons of animals right now as well as we investigate the application space, where shape of the animal's bones, the skull, for example, is radioactive for a better calibration on the gamma spectrometry detectors. It's a very interesting area. And the other main area we help on meeting the metrology needs of member states is our proficiency testing activities. So we operate really the largest kind of proficiency test of its type now. It's free to participate. It contains a wide range of samples. It typically contains 2 water samples, a vegetation, soil sample, printed swipe samples as well, all of which have natural and anthropogenic radioactivity. We try and make it a one-stop solution for member states. Contains samples for measurement by radiochemistry, gamma spectroscopy, ICP now. A lot of requests to include ICP, and that's one of the growing requirements that we've seen to accommodate mass spectrometry techniques for more trace measurements, particularly as these systems are improving, they're becoming more widely available, more sensitive, and more easy to maintain as well. This has grown significantly over the last few years. This year, we hit a record of 551 participants from 95 member states. That was an increase of just under 7% from last year, which itself was an increase of 14% from the year before. Of our earlier survey that I mentioned, 67% of participants on the survey, about nearly 900 participants, thought that ISO 17043 accreditation, so it's accreditation for proficiency testing, would be useful. And we're about to begin on working to make the proficiency testing activities accredited as well. We'll begin this in earnest in early 2026. As I said, the proficiency test participation has been steadily increasing. And I mentioned that we're moving towards the ISO 17034 accreditation. What this provides is an important mechanism as well for also producing reference materials, as it enables the proficiency test itself to be used as a mechanism to characterize and determine values for reference materials under our existing reference material accreditation as well. Just to mention as well, as member states' needs have increased, we've had to even change our laboratory. So in 2019, we announced the need for a new upgraded facility to replace our older laboratories produced in the 1960s. The concept was raised in 2019. A year later, 51 member states have finally contributed approximately 29 million in extra budgetary resources, and this led to the construction of what is now known as the Curie Microbeacon Application Centre. This really increases the floor space of Turk Laboratory by 4, enabling us to do more to support member states, more trainings, more production activities, more people at the laboratory, and indeed we've doubled our staff in the last few years as well. With this growing kind of need, we've had to increase our capabilities as well.
Jonathan, sorry, we are already out of time. Are you nearly finished?
Yeah,
okay, sorry.
Wrap up. To help kind of support these grant requirements, we've had to increase the number of areas. You see highlighted in red are key areas with 3 new gamma spectroscopy systems, low-level measurements, new isotope ratio mass spec, a new triple quad ICP, and also AAS capability. Again, it's because we're seeing more and more needs for trainings and measurement services to help member states in this area. So to conclude, our job is to help to measure radiation in the environment, ionizing radiation. And we do this through 4 main ways: reference material, provision of reference materials, proficiency testing activities, trainings and expertise, and analytical services. And we're seeing an increasing need to provide a wider range of services, especially reference materials. And you've seen some of the thoughts and requests from member states in this presentation as well. I do know as well, I also, on my last slide, had the ISO 17034. Need to adjust that. Apologies. So with that, thank you to everybody for your attention, and I'm happy to answer any questions.
Okay, thank you. Thank you for the invitation to present here today. My name is Stephen Bell. I'm from the Nuclear Metrology Group at NPL in the UK. So the Nuclear Metrology Group covers primary standards of radioactivity and neutrons. My area is primarily radioactive gas metrology. So I've been asked to talk about how ionizing radiation, the sort of metrological needs for ionizing radiation in the future. And so I thought I'd start by sort of posing a question about traceability. Will traceability change as technology changes, as industrial measurements, industrial needs change? So we're all familiar with this pyramid. So we'll, after the presentation, we'll come back to this one. So ionizing radiation is relevant in many areas of the economy, in industry, society. Too many to cover in one presentation. So I'll be a little bit biased towards some work that we've been doing at MPL. So I'll talk about metrology needs for the new generation of nuclear power. This is a big area of growth in the UK and worldwide, and also for nuclear preparedness, which I guess is not necessarily industry, but it does affect industry if there is an incident. Nuclear energy research and development at MPL. So at MPL, we have a sort of a challenge area around energy and environment. Within that, we have a portfolio of projects under the clean technology banner. And within that, we have a metrology for nuclear energy program that covers decommissioning, nuclear fusion, and the new generation of fission reactors, so small modular reactors, advanced modular reactors. And actually, the work we do in this area isn't just nuclear metrology. We cover a wide range of different physical metrologies. And there's actually 8 different groups at MPL working in this program, from temperature and humidity, obviously through nuclear metrology to electrochemistry. Right. And recently, we've done a bit of a sort of a market survey to try and capture what are the measurement challenges that stakeholders in the nuclear energy sector are facing. What are their metrology needs to address these measurement challenges? The themes, the themes of the future, and also what is the policy and regulation landscape. And so I guess I've highlighted a few things here. So measurement challenges, it's a big challenge making measurements in extreme conditions, particularly high radiation fields, high temperature fields. There's an important aspect around data confidence, data quality. This includes nuclear data, cross sections, etc. There's a need to develop and validate new instrumentation for real-time measurements, particularly for neutrons and gamma radiation. There's always a need for education and training. A lot of the people that had the expertise in building nuclear reactors have retired. And we've heard already in several presentations about the need or the themes around AI and digital twins. This sort of drives backwards and forwards with the need for in situ and real-time monitoring, because this can feed into the AI, and the AI can then predict what the real-time response would be. And as an NMI, we play a role in this. So we can support the experimental design and validation of equipment and plant. We can develop independent metrology standards that are aligned with the modern technologies. And we definitely play a role in the education and practical standards to guide this new sector. Okay, so I've got a few sort of case studies of where MPL are supporting research in these areas. So the first is for fusion and specifically tritium measurements. So I'm sure we're all familiar with a fusion reactor. The reactor is fueled with deuterium and tritium in the core. So this is, I guess, a typical fuel cycle for a tokamak style reactor. We have a breeding blankets. Reactors need to produce their own tritium in order to be sustainable in the future. And there's a need to recover the tritium that's exhaust from the tokamak and recovered from the breeder blankets, purify that, separate it from other isotopes, and then re-inject it back into the reactor. And so on this basis, we've been working with the University of Liverpool, who've developed a family of porous organic cage materials. These are, I guess, similar to molecular sieves. They can trap gases. The beauty with this family of materials, you can tune them. So you can tune their selectivity. So you can design them to be trap specific gases or specific isotopes. The trapping mechanism is through kinetic quantum sieving. And essentially at cryogenic temperatures, the selectivity of the powder varies with the de Broglie wavelength of the molecule. So the different mass of the molecule will have a different size, and then that fits into a different pore in this cage material. And so to test these powders, Liverpool approached MPL and asked us if we could build a rig to test the powders. And we've been working with Atkins Realis, sort of an engineering firm, to build a series of rigs, which are essentially comprised of a gas supply, cryostat to cool the powder down, suite of analysis equipment, and then some way to discharge the gases. And so we load the powder into the cryostat, we cool it down to around 60 Kelvin. We inject a small quantity of mixed hydrogen, deuterium, tritium in a neon or helium carrier gas. Hopefully those gases get trapped. We then heat up the powder and see one gas come off over the other, and hence get some separation. So this is a photo of the rig that we've recently built at MPL. We can see the sort of the gas handling equipment, the cryostat, and some of the electrical control panels. The rig has, at the moment, 2 instruments for measurements. So we have a tritium monitor. So this is very sensitive for measuring tritium, but only tritium. We then have a mass spectrometer, which can measure protium, deuterium, and tritium, but its sensitivity is limited by the fact it has a carrier gas. And we're investigating Raman spectroscopy, which has the benefits of being very compact. It can be an inline measurement. You don't need a carrier gas. And so I guess the take-home message here is the metrology need here is to be able to measure not just radioactive things, but also inactive species at the same time, and not compromise your metrology by measuring one with one instrument and one with another. So here are some results. So as I said, we've injected a small quantity of mixed isotopes, hydrogen, tritium isotopes. They've been trapped in the powder. We've then started heating. And what we've seen is if we vary the heating rate, we can start to improve the separation of the gases. So under rapid heating, we get no separation. We slowly, the black traces the temperature of the sample. If we slowly heat it, we start getting the hydrogen off first before the tritium. And then if we heat even slower, we get even better separation. So this is it's an area of growing interest in the fusion world to be able to separate the tritium from deuterium mainly. So we're keen to sort of upskill our metrological capabilities in this area. And actually, this is an area where we think a digital twin or neural network would benefit us. So we have a good handle on the input variables to this rig. So we know the gas composition, the temperature, the flow rates, etc. We don't quite understand the response of the rig or the response of the powder, but we do have a nice back catalog now of results, sort of true values. And so we can use those true values to train this neural network to improve it until we're satisfied that it's accurate. We can then use that to extract the unknown properties of the powder. So its trapping capacity, its sort of intrinsic release temperature, things like this. And then we can go one further. We can start putting in idealized separation plots or functions back through the network and pick out what parameters we need for the powder loading and the temperature profile to get optimum separation. And the idea here is this is a stepping stone towards a pilot plant, and then that's a stepping stone towards a real plant and a fusion power station. And having the digital twin built from the sort of the ground up, embedded in the plants from this point of view is very useful, I think. Okay, another example for fusion, looking at cross-section or the need for cross-section measurements. So there's a big requirement for plasma diagnostics. So the heart of the reactor is a big plasma. The fusion reactor reaction produces helium, alpha particles. It's important that these alpha particles deliver their energy back into the plasma to recover that energy rather than plow into the walls of the reactor and essentially damage those components. So there's a need to study the sort of the alpha losses and the alpha within a reactor. And so this can be done with activation foils containing boron-10 or germanium-76, which can be used to measure these alphas across a wide energy range. Unfortunately, the nuclear data for the cross sections doesn't exist or is poorly defined in some areas. So for the boron-10, there's a need for cross-section measurements at low energies because it's a has a 0 threshold for the reaction. And for germanium 76, there really isn't any cross-section data available. And so we're working with colleagues in Romania to sort of start trying to measure these at the IFIN facility. And this is also of interest for astrophysics as well, for sort of pure research on the triple alpha process. Another example I mentioned tritium breeding is important for the sustainability of fusion reactors. So there'll be breeder blankets containing lithium around a reactor. Flybe is one of the potential candidates. There's lots of research. They haven't defined precisely what blanket they will use, but Flybe is a leading candidate proposed for STEP in the UK, potentially, and for ARC in the US. Now, Flybe contains lithium, beryllium, and fluorine, and all three have isotopes that require improvements in the cross sections. So for the lithium-7, this directly affects the tritium production. For the beryllium-9, this is sort of a neutron multiplier, and we need to understand how many neutrons are being produced to better understand, to better model the reactions. And also the fluorine scatters the neutrons, and this shifts the neutron spectrum, which then has a knock-on effect for the other reactions in the reactor. So all of these cross sections are vital for sort of baselining Flybe as a candidate material. And experiments are planned at NSOF and CERN to start addressing this. Okay, so onto small modular reactors. So a small modular reactor is essentially, it says a small reactor. They are typically in the range of megawatts or hundreds of megawatts compared to gigawatts for a traditional reactor. The idea is to benefit from modern modular construction techniques, so that they can be built in a factory and shipped in large parts like Lego, built on site. The big benefit really actually is the lower upfront capital costs, and in theory, faster return on investment. So that really has unlocked investment in this area. There's lots of designs being pursued worldwide, and I think Russia and China already have reactors running, so well done. There's an opportunity to develop measurement techniques and traceability routes for these techniques and get them embedded in these reactor designs now, rather than wait till they're built and then worry about metrology. So that's a big driver there. And on that basis, we've been working with Rolls-Royce, who've identified that online monitoring of SMR conditions is vital for their business proposition. They need to measure multiple stable and radioactive isotopes in the primary loop, the cooling loop. They want to have minimal operator intervention, minimized in-lab instrument setup and maintenance. And as such, we've been supporting them to develop this analytical solution for online monitoring. We've completed 2 phases of work so far. We're hoping this continues. And then there's an opportunity to investigate other techniques for shorter-lived isotopes, which leads to my next example. So this is an example for monitoring nuclear fuel, whether in core or in storage or even in accident conditions. So this borrows the beta gamma coincidence technique almost directly from the work of the CT-BTO labs. So we're working with AWE, the University of Surrey, and EDF to take this beta gamma technique that's been used for radioxenon, but extend that to radioxenon and radiokrypton that's found in the fission product gases from a reactor. And the idea is that the ratio of these gases give you an indication of the health of the fuel. So this is ongoing work. We'll be doing experiments at the Hartlepool nuclear power station, well, already actually. Okay, so the final example is about nuclear preparedness. So in the event of a nuclear or radiological incidents, there's a strong need for rapid and accurate dose mapping. So if you have uncertain or incomplete dose rate data, you have to be conservative, you have to be cautious. This leads to large exclusion zones, which ends up having very, very high socioeconomic harm. You close factories, you prevent the transport of goods, you prevent children going to school, you prevent people going to hospitals, etc. There's a lot of stress, a lot of anxiety, and even if there aren't indirect deaths from the ionizing radiation, there's a lot of harm from these countermeasures. And so you want to minimize these exclusion zones by having the confidence in your data. So actually, there are two proposals that have been submitted for Euromet JRPs. So they should be being defended today, actually, by PTB and Stuck. And these focus on these sort of improving metrology and for response to a nuclear radiological accident. So, for example, through improving throughput of laboratory measurements, rapid measurements, developing open source frameworks for the modern generation of spectrodosimeters, including AI routines for analyzing spectra, reducing uncertainties and calculating uncertainties, in particular for AI-produced results. And quite more interestingly, I think for me, the recommendations for UAV operations and citizen science measurements. So we saw after Fukushima, lots of people bought these cheap and cheerful radiation detectors off the internet, made their own measurements. As NMIs, I think we have a duty to sort of train and teach people how to make good measurements. And likewise, we may be able to utilize those citizen science networks to get extra data that we can't get from a national network. So I think that was my final example. So I'll go back to the question about traceability. Will it change? In a sense, it will. So it will be a need for increasingly bespoke solutions to niche measurement challenges. There's a drive to embed metrology, so there'll be more sensors in more locations. This will enable automation. So with the inline online measurements, we'll need less human intervention. This will lead to a demand for in situ calibration. So we don't want to remove equipment from a plant to calibrate it, especially there's lots and lots of sensors. And all of this will then underpin and support digital traceability. So digital twins and digital dissemination of standards. And finally, hybrid metrology, as I mentioned, the need to measure radioactive and non-radioactive things at the same time with the same instrument so that you've got the same systematic, you're avoiding systematic uncertainties there. So will the traceability pyramid change? Maybe not. There may be some shortcutting if we have some digital dissemination. Maybe we'll be able to transmit directly from the SI or the primary labs down to the industrial measurement, or maybe not. Maybe the industrial measurements, in effect, become a secondary lab. So that's an open question. But anyway, that's the end of my presentation, and thank you for listening.
Okay, thank you very much. I will try in 20 minutes to give you the full future of dosimetry or dosimetry of the future. I'm not quite sure which is the correct arrangement of words there. So the future of dosimetry is AI. Thank you. Okay, this is the rest of the presentation. Some of you may be familiar with land acknowledgements, and we do this a lot in Canada. So I acknowledge that where I live and work in Ottawa is situated on the unceded and unsurrendered territory of Anishinaabe-Algonquin Nation. Land acknowledgement doesn't change anything just by me saying this, but they're useful to remind us of our relationship to the places in which we have settled. So potential problems of an invited presentation. Quote Niels Bohr, an expert is someone who's made all the mistakes which can be made in a very narrow field. And I will follow that up that a dumb question asked by a recognized expert can be misinterpreted as insightful when it is just dumb. So I apologize when I begin to ask questions in this. So dosimetry problem number one, and François touched on this a little bit. We have a lot of quantities and none of them are ideal for end-use applications. You talk about the kilogram and you just weigh things, but in radiation we've got fluence, we've got air kerma, we've got observed dose to water, we've got observed dose to another material, we've got effective dose, we've got RBA weighted doses, we've got some equations there that you can see. And there's a whole lot of different things that we need to measure and quantities we have to realize to give us what we need for when we talk about dosimetry. So although François said dosimetry is just the measurement of dose and it's really straightforward, no, sorry, that was Vincent said dosimetry was really simple. I think it is slightly more complex. And then the second problem is that we have lots of detectors and none of them are ideal either. So these are just a few of the different things. You've got calorimeters, you've got ionization chambers, you've got chemical dosimeters, you've got film, you've got diode detectors, you've got arrays, and this isn't everything. And we need all of these to do our dose measurements in all the different situations where we need to measure dose. And these really are just here on this image are radiotherapy. We haven't even talked about detectors for imaging or detectors for industrial processing, environmental monitoring, etc. So it is a bit of a problem. And just to reinforce and sort of looking forward, but of course, looking back a little bit, this is an early poster that Alan Jennings created in '95. And we see very early on that there were a load of different detectors and it hasn't got any better. And there's a second poster. And here we see we have a load of units and it's not getting any better. So I will blame the early pioneers for too many detectors and the early ICRU for too many units. But we are in this situation where I think, can we find a solution? And if we're talking solutions, there tend to be sort of two ways of doing it. One is to tinker and modify. So this is where you add another correction factor, you improve a formalism, you might change the name of a quantity, but you're not really making much of a difference. And the other one is to disrupt and rebuild. And this is where you make a radical change to reflect perhaps what is really needed and may not have been achievable previously. And metrologists are inherently innovative, and we've heard it already today, but we're also inherently conservative. And I reckon the ratio is about 50-50. And the cartoon there, we look forward and look back with about the same kind of frequency. So disruption is uncomfortable, and we tend to fall into the tinker and modify more easily. So dosimetry, what do we really want? We're talking about the future. So absorbed dose, as has been said, defined as the energy absorbed per unit mass in some medium. It's a measure of interaction between matter and the radiation beam. Where and when we measure the absorbed dose is often not where and when we actually want to know the quantity. And the quantity we measure is often an analog for the real effect of the interaction that is of interest. So you can interpret that we clearly have a dosimetry problem that needs to be solved. And we can just go through some brief examples to prove that. So radiation therapy. So in this situation, a radiation beam is delivered by a LINAC. You calibrate a beam delivery in terms of absorbed dose to water. The patient dose or what's going to be delivered is determined using a treatment planning system, and the dose received by the tumor is never measured directly. So we do a whole load of dosimetry, but not at the point of interest. And the ultra measurement is not dose at all, it's cell killing. We look at radiopharmaceutical therapy. Treatment involves injecting a drug. Calibration of the injected activity may have traceability to national standards, as I think was heard in the workshop yesterday, where in some places there is, other places there's no traceability of that. You then have some level of dose determination through imaging and calculation, or perhaps just calculation. And the dose received by the tumor is never measured directly. And the ultra measurement is not dose at all. We can look at sterilization of medical goods. So this is where things like single-use plastics are being irradiated to provide sterility. So that may be using a LINAC, as in the picture there. It might be using cobalt-60 sources. The irradiation geometry, as you can imagine from a box full of gloves or syringes, is inhomogeneous and unpredictable. You don't exactly know what you're getting when you stick a box of stuff onto a conveyor belt going through an industrial irradiator. Point dosimeters, as the alanine pellet there shows, are used to validate the process extensively. And you sort of see the standards there underneath of multi-point dose measurement to try and get an estimate of the dose that the actual product gets. And the dose received by the syringe or the glove or the mask is never actually measured. And the ultimate measurement is not dose either, it's sterility. So what do we really want? And this is where we've perhaps been guilty. Dosimetry is focused on quantities that can be clearly defined and easily measured. And I use easily in inverted commas because we know these measurements are not always easy. This works really well. It provides a strong basis. All the national labs can demonstrate what they can do, and we can all compare and prove that we're doing the same thing with similar precision. So it's a great basis, but then we've left the transfer to the final quantities to other people. We've said our mandate is measurement of a clearly defined quantity, and we stick to that. So standard setting organizations, professional organizations, expert panels, often with support of metrologists, have taken this up to make that leap from the thing that we measure to what is needed at the end user. The question that we ask here is, can we or should we get closer to what the end user needs for the accurate implementation of their application? What is the right balance between focusing on really measuring the physical quantity and delivering what the end user needs? And this all comes down to what I would like to refer to as converters, and we know what they are. Common way, we convert from one quantity to another. So converter is the average energy to produce an ion pair that converts the ionization to the air kerma. Specific heat of water converts temperature rise to dose. G value converts the optical density to a dose measured with that. Quality factor converts dose to effective dose. And those have got associated equations, and we're all familiar with them, and we kind of maybe don't see that there's always a conversion. We're never really measuring dose, we're measuring something else. So how far can we convert and still claim traceability is a question. And I would say for conversion, we need two things. We need the mechanism and we need key data. So converters can be things like Bragg gate cavity theory that converts from the gas to the medium. It can be a KQ formalism that changes us from cobalt-60 to whichever beam we're using. And those often need key data, things like recommended interaction coefficients, consensus energy dependencies, etc. And so that brings us, hopefully within time, to the converter. And this proposal is that we actually use particle by particle simulation. So we have one quantity that we can measure, we have one quantity we need, and we get from one to the other through a simulation that is based on data coming in and a geometry that you know. And this is nothing new. I have not told you anything that you don't already do, except that I'm suggesting that we move to this as a universal formalism. And if we have confidence in the simulation, then Q1 does not have to be a dosimetric quantity, and Q2 can be anything we want. So simple, Q1, we measure the activity of an iridium-192 HDR source, and Q2 through simulation from knowing the activity, we calculate the absorbed dose to water. And this is similar effectively to radiopharmaceutical therapy. The harder version of that is that your quantity one is the proton pulse emitted from the anode of a synchrocyclotron. You simulate the whole thing through, and your Q2 is the double DNA strand break. So those are kind of the two extremes. And I'm saying that if simulations can be good enough based on the correct geometry and the correct data, then it may be possible. What are the challenges for this? If it's going to happen, we must have necessary key data with demonstrated traceability and uncertainties. We must have procedures to verify simulation geometries. We must have a standard way to estimate simulation uncertainties that is robust as for current experimental techniques. We must have an agreed system of validation for simulations. And that bringing those all together would give us confidence in what I would call a new dosimetry. So coming back to this, as I said, beyond the idea of a big step from Q1 to Q2, this is a small modification to what we already do. So it's nothing big in that respect. But it is disruptive if we go beyond dosimetric quantities for Q2. So going beyond dose to, say, cell death or chemical modification. And if Q1 is no longer a dosimetric quantity, or if we go beyond our current simulation framework. And so the future of dosimetry is validated AI. And what should our response be to this? So Cicero said, nothing is so unbelievable that oratory cannot make it acceptable. So that means that I could have told you a complete load of garbage and you can reject it. But that's the whole point of this kind of question. At the same time, Marston Bates says, research is the process of going up alleys to see if they are blind. So yeah, it could well be that this will not work, but I think we'll learn a lot if we look into those issues of validated data, uncertainty analysis, validation of simulations that will still have value. And finally, I will quote myself, as an experimental physicist, I'd really like to be proved wrong. So thank you very much.
Okay, thank you. And I would like to give a presentation about the vision for the radionuclide metrology. Okay, so for my talk, it will start from the challenges. And yesterday, we have a very nice workshop about the challenge. So I hope that my talk previously I prepared will reflect the challenge from very close to yesterday, what we're talking about. So for radionuclide metrology, we already have many good works, but still face many challenges. For example, the extreme measurement conditions or very complex conditions. And the very complex of the real world samples or calibration conditions. And also when we talk about the traceability or accessibility of some reference systems like the SI-R30s or something. So we also have some challenge for this, we will talk about later. And the trustworthiness of the algorithm, the critical needs for better nuclear data in our fields. So the first is about the extreme and complex measurement conditions. As we know that now we are often face the very ultra low activity levels of the measurement of the activity, or for the medical nuclides, it's very often to have the very short-lived half-life. So also we have some complex decay or the decay equilibrium of the decay chains. So it's we need a very advanced model of the decay chain, and quite often that we don't have the ideal measurement conditions. So like the geometry, the temperatures or some temperature maybe sometimes it's have some impact. So the radionuclide metrology is increasing required to deliver reliable measurements under non-ideal or time-critical conditions. And for the complexity of the real-world samples, yesterday we have a lot of discussion about the real-world conditions, calibration conditions, and also the samples like in environment radioactive analysis that we have a lot of different matrices of the samples, and we have the impurities of the samples, and we have the homogeneity. So the real world samples is quite different from the calibration conditions. So a challenge is to fill the gap between the reference measurement conditions to the real world condition. And also for the global traceability and accessibility, as we know that in our fields, we have several international reference systems like the SIR, the ESIR30s. And for this, we already have very highly successful for the long-lived or well-established nuclides, but for short half-lived nuclides, like the medical nuclides, we have an increasing need for the comparison, but we don't have we cannot cover all the we cannot cover all the needs in our fields because of the some reasons like the transportations or something like this. So the deconcentralized RMO coordinate SI-30 framework is essential to extend the traceability or the accessibility to our fields. And also, now we are very heavy on the relies on the digital electronics, and so we built the algorithm for analysis, for singular processing, for activity estimation. So it's based on the algorithm-based driving software. So it's very critical in radionuclide metrology now, and to build the trust for the algorithms, it's very important. It's increasing demand for our field for the validation. And another challenge is about the nuclear data. We know that we use the data very often, and for many of our methods, the primary standardization method is based on the nuclear data, like the TDCR calculation. So we use a lot of data, dozens of or even hundreds of the nuclear data. So it's very often that we have the inconsistent experiment data from the database. We have very unreasonable uncertainty sometimes for the data. That means, yeah, the data was the quality of the data is not so good. And for some of the data, we lack of the data. We don't have the data, like the subshell X-rays or something. We don't have enough experiment data, and also the limited digital accessibility of the data. Recently, we have the DOI of the data, so it's improved, but still we need the accessibility of the digital nuclear data, like the motion readable nuclear data. So these 5 aspects are some of the challenges that I thought about that we may still face, and we need to address this kind of the challenge. So next, it's about some selected technology which may shaping our future. So first, it's about the detector technology, and after that, I will talk about the materials, and after some new technology like the digital transformation or machine learning, something, yeah. So for the cryogenic detectors like the MMC or TES, now it's very popular in our fields. So it's maybe not a very new technology, but it's very important technology because it's offering very high resolution and can direct measure some fundamental nuclear data, like the beta spectrum, like the X-ray spectrum, like X-ray the subshell X-ray energies and branch ratios, or even to directly measure the electron capture probabilities. And another technologies, it's not new in many other fields, but it's new for radionuclide metrology, like the mass spectrometry, because it's very sensitive and high selected method for the determination of major, minor trace, or even ultra trace components of the activity. So these 2 detector technology, it's very key technology in our fields. So I will give some examples about the cryogenic detectors. So for example, first features is that this kind of the detector have very high energy resolution. So it can provide the resolution from a few EV for the resolution for X-rays or for some gamma rays. So it's provide a possibility for us to separate the very close peaks in the spectrum to determine some nuclear data like the branch ratio. So it can improve the nuclear data and will benefit for us. So here I just show an example of the data from LNHB's website, it's compared to the semiconductor conductive detectors like the high purity germanium detector. So the resolution is about 10 times higher, better than the semiconductor detectors. So the second example is to use the cryogenic detectors to measure the beta spectrum. So recently, in many of the metrology institute, we do a lot, not so many, do several, do some measurement about the beta spectrum, like for some selected nuclides, like the carbon-14, the cobalt-60, the technetium-99, or some nuclides. So for this, we have the possibility to measure the beta spectrum. Also, we provide the experimental spectrum as a reference to improve the calculation. As we know recently that for the calculation of the beta spectrum, it's quite critical in the very low energy. If we don't have the information in the low energy, we don't know the real spectrum. In the very low energy, we observe that the probability of the beta spectrum is higher than what we expected due to the atomic exchange effect. So now we already addressed the problem of some kind of the transitions like the Arnold transition, but for many other transitions, we still have some difficulties. So this is another example we did recently that we measure the lead-210 nuclide and to measure spectrum. So which is quite interesting that we can shift the spectrum over the threshold. So it's a threshold-free beta spectrum. And from this, we can observe the spectrum from zero energy. So it provides a very high quality experimental spectrum for the beta spectrum of the first forbidden non-unique transition. And so for this data, we improve the atomic exchange model, and we improve the nuclear data like the Q value, the branch ratios, and the emission probability of the inversion, internal conversion electrons. So we ask our colleagues to calculate the beta spectrum by the well-developed, previously well-developed code like the beta shape, but we found that it's a big bias from the calculation to the experiment. So based on this experiment spectrum, we improved the calculation. So it's a very good technology to provide the experimental data to improve the theory. And this detector can also be used to do the absolute measurement of the activity like the decay energy spectrometry. So this is an example from NIST. It's recently, I take this example from the website. So it's recently that they made some measurement for the AM241 source, and it can be used to do the absolute measurement of the source, and can also be compared to traditional method. Okay, so this is there are some examples for the next generation detector technology. So I will move to the detection materials. So as you know that for materials now we have several very innovation materials like the metal organic framework, the CDT detectors, the perovskite materials. So it can enhance the performance in energy resolutions, the response speed, or some other performance, and so it can address a lot of the challenge in our fields. There are some examples that the scintillation porous metal organic framework materials, it can be used to measure the radioactive gas, very sensitive materials, to measure the radioactive gas, because the radioactive gas is not so easy to measure in our fields. And if you compare the two fingers, you can see that the sensitivity is much higher than the traditional material. And another one is the nanoporous in organic scintillators. It's also a study from our colleagues from LNHB. So this kind of the scintillator can be used to measure some low energy beta emitters and to do the real time and discrimination of the radioactive gas mixture. So it's a very good materials and can be used for some special applications. And what will be even more interesting is that I found, so recently, some colleagues developed the 3D printed plastic scintillator. So you know that with a 3D printer, previously we can only print some structure materials, but not for detectors. Now we have the possibility to print the detector directly. So we can design the very complex geometry of the detector and to make it in special applications. Okay, now I would like to move to the digital transformation and the radionuclide metrology. So yesterday I already talked about this. I will briefly introduce it again. So the digital transformation is, we have two aspects. The first is the digital transformation for metrology is to use the digital technology to modernize the metrology itself. So we have several, dozens of the digital technologies, so like the digital acquisition, digital twins, and also the AI. We can also think about it. It can be classified as the digital technology. And some examples that, for the digital acquisition that we introduced of this in our fields quite early in 1990s. So our colleagues use the digital acquisition to digitize the signal. And after that, we can do software-based analysis for signal processing. So it's quite flexible and it's quite useful for kind of the measurement, since we are acquiring the data in once, but we can analyze the data after. So for some short half-life nuclide, it's very critical to use this kind of the technology. And also some other examples is it's just recently we're also doing something on this, that we use the digital acquisition combined with the software-based analysis. We can define the function of the instrument by software, like the digital coincidence counting or digital selective sampling method. And also, we are very interested about the digital data set, which can be used for the algorithm comparison to build the trust for algorithm we developed. So if we compare the difference of the conventional comparison and the algorithm comparison, the difference is that the conventional comparison is based on the measurement of the distributed radioactive solutions, and the algorithm comparison is based on the analysis of the distributed least mode dataset, digital dataset. So based on this digital dataset, we can do the analysis and do the comparison to validate the algorithm we developed. So the data can come from the experiment or come from the simulations. And from the experiment, we can see that we do some algorithm comparisons based on the digital, based on the experimental data set. So from the result, we see that based on this kind of the comparison, we can achieve relative difference between different methods less than 0.03%. That means it's much better than traditional comparison, because we cannot achieve this kind of the relative deviations by traditional comparison. This is a way to build the robust comparison against the statistical fluctuations. And also based on the simulated digital data set, we can also doing this kind of the algorithm comparison, and it's even better to rigorous validation of the algorithm. And another aspect is about the metrology for digital transformation. We can use the metrology to ensure the trust and the reliability of for the digital technologies, like the digital metrology service, digital standards, digital semantics, traceable reference data. So for this kind of fields that, as I talked about yesterday, in the CIPM, we have a forum on metrology and digitalization. So in this forum, there are several task groups and working groups to address this kind of the technique to use the metrology to support the digital transformation. And in radionuclide metrology, we have some examples like the DCC for radioactivity measurement, the digitalization of the service categories, and also some examples for the machine learning. So for the machine learning, we have so many methods like the regression, the classification, the clustering. So just two simple examples to show. To use the machine learning, we can discriminate the background and the real events. So based on very simple machine learning method like the support vector machines, this is one of the very basic machine learning method. We can achieve a very significant reduced background, but still we keep the detection efficiency. So this is the benefits. We not only reduce the background, but we still keep the detection efficiency. And another example is for the alpha beta discrimination. So we compare the traditional method like the PSD method and also the machine learning method. So PSD method is the pulse shift discrimination method. So it's very often that we cannot separate the two signals very easily. But based on very simple unsupervised machine learning, or even we just use the dimension reduction technique, we can easily separate the data. Okay, this is a conclusion that the radionuclide metrology is entering a transformative phase, driven by advance in new detection technologies, new materials, the AI, and the growing focus on real-world application. So the vision for the future is to integration of the state-of-the-art technology hardware with the intelligence software to solve the main challenges that we cannot resolve in the past. So, okay, this is my talk. Thanks for your attention.
Yeah, thank you very much. So now we will hear about something about neutrons, neutron metrology and the challenges. But before I come to the challenges related to neutron metrology, I want to first give a motivation and ask the question, why do we do metrology at all for neutrons? And the first thing you think of if you hear about neutron metrology, neutron dosimetry, is of course nuclear power plants. That means the creation or the, of energy via spallation in a nuclear process. This is of course one of the main drivers to invent neutron metrology after the development of nuclear weapons, of course. And in all questions related to the fuel cycle, that means storage and so on, are of course, or were of course, an important driver for neutron metrology. But my message today should be, or is that neutron metrology is much more than just nuclear power. As we heard already today, a few examples, neutrons play a role in medical application. We heard the example of BNCT, which I will explain later on also, or mention also in my talk. Then, of course, neutrons are part of the secondary stray radiation in high energy photon applications for medical treatment. If you have patients which are treated with hadron, high energy protons or carbon ions, you have neutrons as secondary particle. Nuclear fusion, we heard about from Stephen about nuclear fusion, a process in which neutrons play the main role of bringing the energy out of the plasma into the first wall and so on. And there you have a lot of neutrons. So this is a new field of research and industry which is growing up. ITER is built. So also there, neutrons are very important. High energy accelerators always produce neutrons. So this is a picture of the Atamba Lab facility, 200 MeV proton accelerator in South Africa. About all research accelerators here, GSI in Germany or CERN, or if you have more higher energies of the primary particles, you will create neutrons, which you have to measure either for radiation protection purposes of the workers and the researchers in these facilities, or for scientific motivations. Even in underground labs, here in Gran Sasso, in neutrino physics and so on, you still have neutrons. So even a few kilometers below the surface, muons can reach these depths and produce via spallation reactants neutrons, and their neutrons are a background in these fundamental research experiments, where they, so to say, simulate the events which you are searching at. If you want to look for weak interacting massive particles or things like that, you look to momentum transfer, and neutrons can simulate that. That also in these communities, the people need to know what is the neutron spectrum, what is the neutron background to understand the experiments. And then, of course, in aviation, in space, if you want to go to the moon or the Mars, the astronauts will see a lot of neutrons. And if you want to live for a certain period on the moon, and even if you have a shelter, and if you protect the people living there with some material, you can perhaps protect against the primary cosmic radiation, which is mainly caused by, or which is mainly charged particles. But of course, the secondary neutron radiation will still be there and will be the main issue for radiation protection for astronauts. So neutrons are important in a lot of places. And this picture here, I hope you can see my mouse. So to say, is a little bit symbolic that on the left side you have classical things and also lower energies, and on the right side you have higher energies, higher intensities. And in the end of my talk, you will see perhaps that the most challenges are in this range. So even classical neutron dosimetry is challenging. We do not face only challenges like going to the moon or Mars. We just have, with conventional here on Earth, neutron metrology, a lot of challenges. And a few words about that. So neutrons are not directly ionizing particles, but first have to interact with matter to produce ionizing radiation. The energy range of neutron, which is relevant, covers more than 12 orders of magnitude. If you compare that, for example, with electromagnetic waves, it would correspond to an energy range from gigahertz to gamma radiation with several MeV. This is also just 12 orders of magnitude. And this different energy range of the neutron is the origin that the detection of neutron works with very different physics. You have capture of thermal neutrons, you have elastic and inelastic scattering, there are fission processes, spallation reactions of high energy neutrons, and all these principles can be used to detect or to build neutron detectors. And also concerning the intensities, I just mentioned a few examples. In the Gran Sasso underground lab, for example, you have intensities of 10 to the minus 6 neutrons per square centimeter in second. At the first wall of ITER, you have 10 to the 14, which is 20 orders of magnitude. And you can imagine if you want to build a detector in one case, it's hard to find any material which is surviving that. So at ITER, at fusion facilities, so you have radiation hard diamond detectors or whatever. In underground labs, you need to have very sensitive, very big detectors, which you need to understand very well with low intrinsic background, low intrinsic alpha activity or whatever. So then we are in a regime where we are facing, so to say, same problems as with the low radioactivity community. So a few words about the neutron metrology community, the members of CCRI section 3. So at the moment we are 19 institutes from 17 countries covering all RMOs. But the groups are very different in size and in resources. And in total, I would say during our last CCRI 3 meeting in Vienna, we were something like 40 people, which you can hear on the screen. Of course, not everybody from the neutron group was there, but of course the neutron metrology community is limited in resources and cannot cover deeply all the fields which are relevant. And a lot of neutron metrology or neutron measurement is also done outside the metrology community, but often in a non-traceable way. That means research group working in low-level physics, in high-energy physics, the ESA, the NASA, they work, of course, on problems related to neutrons, but often they do not have any link to traceability. And this is, so to say, also one challenge which we somehow have to bridge. Before going to a few more open questions, I just want to say what is, so to say, really established. I would say the best understood measurement principle in neutron metrology is the measurement of the emission rate of neutron sources with the manganese bars. It was already mentioned here also today. Here you can achieve an uncertainty in the order of 0.5%. This is just a picture from the installation at NPL. In principle, it's a full absorption experiment where all the neutrons coming from a small source are moderated in a water tank and then captured. The thermal neutron are captured in the manganese solution, and so you relate the neutron emission rate to the radioactivity standard. But even in experiments like that, you have correction factors which are in the order of 2. That means 50% of the neutrons are not captured in the manganese, but somewhere else or escaping or whatever. That means also these experiments heavily rely on Monte Carlo simulations, cross-section, and everything which is related to that. Otherwise, you are not able to determine a correction factor which is in the order of 2, or only 50% of the neutrons are detected within a 0.5% uncertainty. And the good thing is that even with all these challenges, this method is working. In the last comparison, no, I don't have the picture here. The last comparison, we had something like 10 participants all over the world with very different instruments, which had very different correction factors, size, diameters, manganese solution, and so on, concentration. Nevertheless, it worked well, and so I would say this is established. We still face the problem that sending around a californium source nowadays as radioactive material is not so easy if you want to send it to all continents, more or less. But to really test it, I do not see a good alternative. Just with simulated data or list mode data, I would say it would make no sense in this case as the instruments are so different. What is also established is the neutron metrology for monoenergetic neutrons in the energy range from, let's say, 20 keV to 20 MeV. These neutron fields can be produced with low energy accelerators, which you can buy from companies which are owned by several NMIs. And here is an example of a key comparison for monoenergetic energies up to 15 MeV. The detectors are based on NP scattering, on neutron scattering on carbon, on hydrogen, and on moderating detectors, which then detect the thermal neutrons. And here you can determine the key comparison reference value with an uncertainty of 1 or 2%. And I would also say there are still small technical problems, but more or less this is also established. But these detectors and these principles are, so to say, established up to 20 MeV, and above 20 MeV, it becomes more difficult. Neutron metrology relies on cross-section, especially on a few reference cross-sections, which are well known until 20 MeV. Above, there is good data for uranium 235 and 238 fission, which works partially up to 200 MeV, but above 200 MeV, I would say this picture is empty. So we do not have any good data. We strongly rely on models, nuclear physics models, not Monte Carlo models, but really modeling the nucleus. And of course, there you have very big uncertainties. So I'm not an expert in nuclear theory and so on, but it is not, so to say, I would say, metrological level just to rely on pure statistical calculations or things like that. Concerning neutron dosimetry, we learned from we learned that we have a lot of quantities, we have a lot of detectors, and nothing really fits together. Classical neutron dosimetry up to 20 MeV is working quite well if you have an idea about your neutron field and if you know the response of your detectors. What you can see here are typical fluence to dose conversion coefficients for neutrons, and in red you see the curve of a conventional available instrument. It more or less fits. There are certain energy ranges in the thermal, in the epithermal, in the high energy part, where there are strong discrepancies. That means if you just put your detector in a field, in an unknown field, you will get something, you might get something wrong with a factor of 2. But if you are able to measure the neutron field with a detector like a monosphere spectrometer, you can determine the neutron dose much better with something like 5 or 10% uncertainties. But also here you have the problem that these detectors can be characterized with the monoenergetic reference fields, which were established, where we have key comparisons, but only up to 20 MeV. And again, above 20 MeV, higher energies, all the response functions of these detectors, which are used to characterize unknown fields, are also just based on models and assumptions. And for, I would say, operational radiation protection, there are, so to say, solutions to increase the sensitivity of commercial devices in the energy range above 20 MeV by putting a lead shield around a conventional detector, which makes the situation not perfect, but at least good enough for radiation protection level normally. So what is established? I would say classical neutron dosimetry metrology up to 20 MeV with moderate intensities, with constant fields which are not pulsed, which are slowly varying or homogeneous, is more or less okay. The rest, I would say, we face a lot of challenges, and this is still a lot of things to work on. The energy range, as I said, 20 MeV is more or less the limit, but in typical fields around high energy accelerators, which you can see here on the bottom, the neutron spectrum in the upper atmosphere, more or less 50% of the neutron fluence can come up of is represented by neutrons having energies more than 20 MeV. And this is the typical spectrum. You have typical in a thermal peak, you have some epithermal neutrons, and then you have a high energy part at around 1 MeV, and you have higher energy neutrons. And this is a situation which you will face in very different fields, around high energy accelerators, medical accelerators, if we speak about proton therapy, in the upper atmosphere, in spacecraft, and so on. So this is really the energy range which is challenging and which we need to investigate. Here also, as I said, we can measure, but also the response of the detectors rely on Monte Carlo simulations, and we do not have any calibration fields to verify that. A new application of neutron metrology for environmental things is, so to say, that the neutrons coming from the upper atmosphere are used to measure the water content in soil. And the basic principle behind it is that neutrons are scattered in hydrogen, and that means the backscattered neutrons strongly depend on the water content in soil. And the field of cosmic neutrons is all over there, all over the place in the whole world, with a different intensity, of course. But if you put a very sensitive neutron detector a few meters above ground, you will see a difference in the counting rate if it's raining or not raining, or if the soil is humid or not. And you can reverse it, and you can say, okay, I measure, I calibrate somehow my detector, and then I can measure the water content in soil for farming applications or things like that by just measuring the backscattered neutrons. But also here, the intrinsic spectrum, which comes from the cosmic neutrons, shows a very strong permanent peak of high energy neutrons. And to fully understand the system, also you need to know the spectrum. There are a few facilities in the world which can produce high energy neutrons above 20 MeV up to maximum 400 MeVs. But all these facilities were originally built for other purposes and are not really metrological suited. We need to characterize a neutron field to use it for calibration purposes. We need to have a pulsed field with a well-defined pulse structure. We need a long flight path, we need a low background, and of course we need access. Usually these fields are, as I said, were developed for other applications, for research, and operating facilities which are able to produce these high energy neutrons cost a lot. So also there's a question how NMIs, external users or industry could get access to use these fields later on. Okay. Another field which I just want to mention is pulsed neutrons. There are certain developments covering that problem or that challenge by having dedicated electronics or using passive detectors based on activation. So also to activate special materials and later on investigate the radioactivity is the principle of detecting neutrons. But here again, this is working if you have, so to say, energies up to 20 MeV, but above, you still have, again, the same problem as I just mentioned. And the last thing, and then I come to my conclusion, is BNCT. The principle was already explained. Concerning neutron metrology, the problem with BNCT is that we have very strong inhomogeneous neutron fields in an epithermal range. Usually these fields are below, so above thermal neutrons, but below a few hundred keV. And this is an energy range which is usually not covered by monoenergetic neutrons, where we do not have any reference fields. That means you have to develop detectors, you have to characterize inhomogeneous neutron fields, you have to measure the spectrum, but you do not have to, at least at the moment, you do not have any possibility to characterize and calibrate your detectors. So the spectrometry is difficult, and again, you face a problem of very high intensity. So in summary, the challenges in neutron metrology are the following. We need really a high energy reference field, including new detectors and to perform comparisons. There is, so to say, above 20 MeV no traceable neutron metrology. We do not have any CMCs. So everything above it is just outside the MRA and the metrological community, so to say. High intensity fields are a challenge, fusion, material science, and so on. Pulsed neutron fields, usually these medical fields which are used for treatment of patients are not steady state, but often are pulsed fields. And there are new applications which also need metrological support, like in the medical thing, BNCT, or new methods like cosmic ray neutron sensing, where you use cosmic neutrons to learn something about the water content in your environment. So a lot of things to do for a small community, and yeah, that's it.
So just a question, after all what we have seen about what could be a future for in every field, in every sections. The question is what the BIPM could do to answer to that in this way. So just remember this picture I show you. So we are just focused now on this small part of the whole system, which is the BIPM. And the BIPM has 3 missions to provide comparison and calibration services that can be centralized in a cost-effective way. So that's what we are looking. To coordinate research projects of international interest, and to organize knowledge transfer and capacity building activities. So that's our 3 main missions. And for that, we have a team of 9 people. So you have seen them, but I will give the names and you will know. So you have Cécilia Kessler, you have Philippe Roger, you have Anna Willewald, Karine Michotte, Romain Coulon, Manuel Denis, Stéphane Choteau, and Sami Kourdzeh, and at the end me. And these 9 people, what they do is on-demand bilateral comparison and dosimetry calibration services for the member states. All what we have done have been developed at the request of the member states through the CCRI, and we perform about 20 comparisons and 25 dosimetry calibrations per year, which is small compared to what NMI produce every year, but we do it in order to, with our availability, and to go to a BIPM comparison is not just going calibration. So that's why it's a number. We perform, when we have time, research and development to expand or optimize these services. We follow the needs expressed by you. And generally, if we have to perform projects, it's generally done in collaboration with NMIs and DIs, which generally have not the size to undergo a full research development without secondments, without your helps. And the main goal is to support the ionizing radiation metrology community. So the CCRI, the sections, the working group and task group, organizing workshops as of today, webinars in collaboration with the CCRI, scientific and technical support if you need, and developing and facilitating cooperation between the NMIs and other organizations like the EAEA, the CTBTO, I think. Okay, so in radiation dosimetry services, so our services is bilateral comparison and calibration for a range of beam energy, covering radiotherapy, diagnostic, radiation protections. We have a world-leading reproducibility fields. It has been, due to that, it has been accepted by the CCRI in 1999 to serve as a 𝐏𝐫𝐬 for everybody in dosimetry. And this is also defined a long-term measurement cycle. So we need to have also a very good reproducibility. So that's why it is. And the benefits we have now, and dosimetry people can assess that, a robust international measurement system for them, and a well-defined 𝐏𝐫𝐬. So this is a picture how it runs. So just see that BIPM is at the center, everybody connected to BIPM, and then other RMO comparison connected to this RMO, and EAEA also participating to some RMO comparison, getting traceability indirectly in that way. So we have 9 international reference systems for dosimetry, air karma, absorbed dose to water, with primary instrument standards. The facilities, we will have opportunity to make a visit for those who do not know. This evening, you have a choice, reception, eating and drinking, or visiting. You do what you want. That I'm sure to have the most interested people. And so I will not detail, but X-rays and cobalt-60 source and off-site facilities, we use a high-energy photon, so LINAC as a DOSEO facility, not far from here. We use a cesium-137 source as the EAEA, and for the brachytherapy, the BIPM as a transfer instrument and goes each NMI places for that. In radioactivity services, we do not measure in the primary way the activity, but what we do, it is a permanently open comparison, and we recalculate each time there is a measurement, the 𝐏𝐶RV for each isotopes. And this is done through an equivalent activity that we are measuring, these samples are sent by the NMI's DI. So NMI's DI, they send their impulse, they have measured with a primary standard the activity, and we put it either in the SIR, you have heard about it. So it's 50 years old, a lot of comparison, and the application of the radioisotopes that we measure with SIR is nuclear medicine and environmental protections. Or if you have short-lived isotopes, then it is a transportable or transfer system, as for you, Ralph. And so this CRT comes just near the production, and we measure on site. And this has been started since 2009, and mainly for nuclear medicine applications. But Sometimes you have isotopes that cannot be measured with both the systems. So that's why the extension of the SIR has been done. What is in that case done is that you take the ampoules, here at the BIPM, we take a few drops, we put it in the liquid scintillation system, and we put it inside the SIR. In such a way, you can measure pure beta or alpha emitters. And that just started beginning of this year. And it will be application also for nuclear medicine and environmental protection. For the capacity building and knowledge transfer, so we perform that during the bilateral comparisons and the calibrations. People coming as a BIPM with their instruments, they can get some knowledge exchange with us. Also, it's important for small NMI SDIs when there are 2-3 people only working in ionizing radiation metrology. It's important that they also have a place where they can get some knowledge by exchange with people. We also are part of the SSDL scientific community to maintain the communication between these two networks, and we also having more and more students and PhD from other institutes in order to work with us. Knowledge transfer, so participation to schools. For last one was this year, Urados Bucharest metrology school about metrology and radiation dosimetry measurements, and the CCRI webinars, which is something which is running very well. So we try to have 5 to 8 webinars per year. And at the end, the conference and the workshop, we participate to scientific organization and organization committees. So for example, the IDOS in Vienna next year at the EAA, we are participating to that. And the ICRM this year, we also were completely involved in the preparation and participation. And the CCRI workshops, we can co-organize and even host as of today these workshops. So why a long-term strategy? Because we have to identify the challenges. I explained my directors this morning. We are preparing the next 4 years work program, but we would like to have also a vision on after that. And also there is long-term projects. If there are long-term projects that we need to have a vision of something longer term. Also anticipating future changes. So since last year, we are in the process of renewing progressively 5 over 9 now of our staff. So we need to match the expected required skills with existing expertise, managing BIPM staffing budget, better aligned with CPM strategy. And so that's why I will not go there. So there were a lot of meetings, a lot of workshops all the year, including ECRM, including sections meeting. We always group section meeting with workshops, and everything is in order that today and tomorrow we try to have a good picture of what could be the future in order to go to 2 things: update the CCRI strategy and also finalize the BIPM IR department strategy related, because the BIPM future activities are fully dependent on the future needs of the member states. We are not decided what we do. It is, if you want, we do something, we will see if we can. That's the answer. Okay, so future developments, I will speed up. In dosimetry, maintain and update existing services, develop new services, strengthen the links with EIA and SSDL, and explore alternative standard fees for replacing eventually the cobalt-60. Radionuclides, I will have slides after, but broaden the measurement capabilities with a reference system, involve the EIA further, participate to better nuclear data and new technologies. Neutrons, so you have seen the last presentation. The problem is that they need to access big facilities in order to make all this new challenge they are facing off, and we can help them to find entrance, how to access these facilities. And we are successful because GT Jensen has sent a letter 2 weeks ago, and after 2 weeks, we have 2 facilities and we can go there. So that's running that way. And define also faster comparison scheme. We will try to involve more the RMOs in order to perform at their level also comparisons, because neutron comparisons cannot be done in the bilateral way. So it's spend a lot of time and energy to manage that. So to involve also the RMOs, and Uramet will start, thank you for that, Linda, to establish neutron comparison at the RMO level. So co-organize CBKT, so co-organize support of CCRI workshops, training and knowledge transfer, webinars, and also something I will not speak about later, but digital, of course, will have also a large impact of what we will do. Digital electronics for the radionuclide metrology at this time, new development for primary methods apply with digital electronics. But we are also thinking to centralize services, like, for example, How can we validate digital measurement data analysis method, simulation codes? What can we do in order to compare simulation code or simulations themselves? So we have to think about with you and how can we build that? And if we can host at the BIPM something to help you to get this information, we'll be happy to do that. And the support to digital transformation. Okay, just a few examples. Last CCRI one, we had some discussion. Could be, if because some needs are rise up, that we have to develop a facility for iodine 125 brachytherapy. So something that example here from India, what they have done, so something similar. Potentially, we could also develop new X-ray fields around 80 keV in order to complete the field we have as reference field. And if we want to replace in the future cobalt-60, how can we do that? So I just give you an example of a French company which produce X-ray beams up to 1 or 2, 3 MeV. Or if we can do it at 1.2, why not? But is it relevant or not? This is all these questions we have to think about. I don't want to give questions, but what we have to think about. For the long term, so some people in the room will recognize this picture, depending on the request made by the CCRI and in collaboration with the NMI, if there is a need in the future, maybe we could develop at the BIPM such a system like the NPL graphite colorimeter and use it in order to go to facilities and make comparison like that, if this is of interest for you. In the emerging fields, it will be the same thing. Should we or should we not, in the future, develop centralized services by the BIPM for high energy electrons, for flash radiotherapy, for mini microbeams, all these questions. But once more, we will have to discuss all together. What we are doing in radionuclides already is to replace the SIR because it's 50 years old. So we have new ionizing chambers. We replace electronics by digital ones, and we have two connected back to back. And all these things together, we have new applications possible, and also we are able to measure lower activity, so that expands the capabilities of the system. For the RMO30, this is also a way in order to share the burden, to share the workload. It has been decided that the system of the CRT was, okay, we make measurement with the SIR, we make a link to the CRT make all the measurement all around the world. But today, we cannot do more than 1 to 2 comparisons per year, and the request rate is larger than that. So it's it will never work like that. So decision has been done that RMO will build their own CRT, maybe a copy, maybe something slightly different, and part of the participants will participate to the RMO one, whereas we will still keep, for those who are not able to participate to this RMO comparisons, CRT will still be there, and the BIPM will still make the connection with these ones. So that will be also allow participation of non-member states and also knowledge transfer, because when we go there, we can explain people how it works. And this is a colleagues from Brazil with Johnny in the room there. Okay. One point also I would like to point out, so in my opinion, we will have to have more and more connection with IAEA. So of course, today it's mostly through the SSDL and the dosimetry activity, but we would like to certainly to strengthen the links. We will have participation in organization scientific committee will continue our dosimetry services for the calibration of their secondary standards, provide reference irradiation of dosimeters that will continue. We are using today BIPM, as a BIPM use the cesium-137 irradiator of the IAEA. Could be more in the future. This is something on the table. But we could also develop a collaboration in radionuclide metrology. So we are thinking how can we contribute to the reference material. So could be helping IAEA to organize supplementary comparisons with BIPM co-piloting and potentially acting as a neutron spiking party. Could also see how IAEA can be involved in providing reference material for mass spectrometry. So we can be there and to also then increase the connection between radionuclide metrology and the IAEA. Enhance the cooperation also for neutrons, because IAEA has a big project to build a full facility for neutrons. Question will be, could we use it also for training people to establish links for neutrons? So that's something also we will have to see. And BIPM can help to facilitate this discussion and collaborate on general topics like engage collaborative work on nuclear data, contribute to technical reports on co-developing together, training, e-learning, and knowledge transfer. EIA has a huge program of knowledge transfer. But sometimes we need just the step in order to reach what is the need for primary labs for that. Okay? The conclusion. We have a few talented and passionate people that are working for you. We are centralized services for member states growing and expanding. We support application for health and environmental monitoring. And we are deeply linked to your community. So CCRI, NMIs and DIs and the EAEA. We have a lot of development perspectives. So this is the list, I will not that. But so it means we have a lot to do in the next 55 years. But it will be done for you and with you, not without, because we need your help for that. Thank you very much.
Good afternoon, dear colleagues. My name is Azamat Dalbaldiyev. I represent Uzbek National Institute of Metrology, shortly UZNIM. It's a great honor to participate in this workshop and share with you our experience in establishing secondary standard dosimetry laboratory in Uzbekistan. First of all, I want to say about our institute. SSDL was established under the Department of Measuring Radiotechnical Quantities, Ionization Radiation, and Non-Destructive Testing, which is one of the 7 departments of Uzbek National Institute of Metrology, which is under Uzbek Agency for Technical Regulation. UZNIM serves as a national body and responsible for the maintaining national standards and ensuring traceability in Uzbekistan. Establishing the SSDL within the institute strengthens the country's radiation protection infrastructure and supports calibration services for medical and industrial purposes. Our SSDL provides calibration dosimeters used in radiation protection, diagnostic radiology. Also, we provide the calibration contamination meters. Also, our SSDL provides reference irradiation for personal dosimeters and disseminate information in Uzbekistan. As you know, Uzbekistan ranks 5th place in the world and the 2nd place in the Commonwealth of Independent States in uranium production. And our country is going to build 2 pressurized water reactor and a small module reactor. This fact underlines that we should build a strong ionization radiation metrology infrastructure in our country. Let's see the development timeline of ionization radiation in our country. In 1960s, the first laboratory for ionization radiation measurement was established in Uzbekistan. In 1995, this laboratory removed to the new building in which we are stayed now. In 2050, under the IAEA Technical Cooperation Program, we developed our metrological infrastructure and procured the standard in our laboratory. In 2022, also under the IAEA Technical Cooperation Program, we established secondary standard dosimetry laboratory. Let's skip 2 years, which I will tell on next slide. In this year, we are developing the standard for the volumetric activity of radon. And by the end of this year, we will develop this standard. In the next 5 years, we are going to build 3 standards. This is a primary standard for the unit of radioactivity. Also, we are going to build laboratory for diagnostic radiology, especially for the mammography. And the last one is a laboratory for external beam radiation therapy calibration. I'm going to tell you the way of establishing SSDL in our country. Establishing the SSDL in Uzbekistan started in 2018 under the technical cooperation of IAEA, originally designed for the 2 years. During the planning, gamma and X-ray radiator system planned to build in 1 room. Due to the pandemic, the installation was delayed and the equipment finally arrived in 2022. And in the September 2022, the radiator system were installed and the commissioning training was conducted. By the end of 2022, full performance tests of the system were successfully completed, and earlier 2023, the laboratory underwent the reaccreditation by our national accreditation body and followed by the peer review by the ERMO COMET. During the summer 2024, the laboratory successfully participated in the intercomparisons with IAEA dosimetry laboratory, and finally in 2024, our laboratory obtained full membership in the IAEA WHO network of SSDL and officially gained the status of SSDL. During the implementation this project, we have learned several lessons. First of all the countries who want to build the SSDL in their country should check all the requirements of the relevant standard. For us, it was a standard of 4037 that especially for the usage of voltage divider. X-ray unit generator and cooling system might cause significant heating of the room that can be caused during the calibration. The time of creation of SSDL may exceed the planned time. And also, each laboratory should check all the types of connectors which can delay the commissioning tests. Also, estimate number and types of measuring instruments that need to be calibrated according to your national requirements. In this slide, you can see the common gamma and X-ray radiators, and you can find the technical specification of our facilities. In our country, we can provide the radiation protection calibration, especially for the N series, diagnostic radiology for RQR, RQA, and RQT series. Also, we can calibrate in the field of CCRI qualities in the mammography fields. Our national standard consists of electrometer and ionization chamber, which are traceable to the IAEA dosimetry laboratory. And all the information you can see on this slide. One of the main topic of in our country is measuring radioactivity. During the IAEA Technical Cooperation Program, we purchased in 2050 the high-purity germanium spectrometer for the measuring the activity. But this year, we decided to use this spectrometer to calibrate our sources. In this year, under the government agreement on providing technical assistance in the field of metrology, signed in May 2024, we got gamma standards, it's point sources, sealed source for calibration contamination meters, and also volumetric photon emitter reference sources. The specification you can see in this slide. Our SSDL, besides of dosimetry, we provide the service in calibration surface contamination meters, also gamma spectrometers in terms of efficiency. And in this slide, you can see that our planned project for the establishing primary standards for unit of radioactivity. One of these methods can be realized in our laboratory. To confirm the calibration and measurement capabilities of the COMET member countries, we initiated the supplementary comparisons for the radiation protection air camera standards, in which 10 countries participated. In this comparison, we used two ionization chamber. First, well known, and the second ionization chamber was manufactured by our colleagues from Nîmes, China, and this is a well way to see the stability of this new chamber. Also, our laboratory initiated the hybrid comparison for the air camera standard in medium energy X-rays. This is a CCRI qualities. In this hybrid comparison, laboratory will calibrate the ionization chamber, and the third party will report the results. For today, Uznim prepared the technical protocol, calibrated transfer chamber, and send the results to the third party. And the transfer instrument was sent to second participant. Saying about our progress and achievement for the last 2-3 years, We participate in bilateral comparison with IAEA dosimetry laboratory. The results you can see in this slide, and I think the result is very well to disseminate the results along in our country. Also, our laboratory participated in the comparison for the Asia countries. This comparison was for the air camera for the photon absorbed dose and the tissue for better radiation protection calibration. In this comparison, 12 laboratory was participated, also including PSDLs and SSDLs. In this comparison, OSLD are data in terms of air camera within the specified dose range. And the results you can see in this slide. Also, the results is very well for SSDLs. In this slide, you can see that our laboratory was included to the SSDL network, and we published our calibration measurement capability for the Uzbekistan for the first time, and we claimed six CMCs. We participate in the several comparisons, including the key comparisons. We published our laboratory in the IAEA's SSDL newsletter, published our results for the testing our system for radiation protection dosimetry journal, and I conducted the training for the establishing SSDL based on the IAEA requirements. Thank you very much for attention.
Okay, hello everyone. Thank you. So I'll start just by giving you a quick introduction to NPL for those who are not familiar. So NPL stands for the National Physical Laboratory. We are the UK National Measurement Institute, and we are a primary standard lab. And before I forget, I just want to mention that this year we celebrated our 125th year anniversary. So I work in the radiotherapy and radiation dosimetry group, where we develop standards and protocols for radiotherapy. And I'll just like to start by giving you some context, by giving you some statistics. 1 in 2 of us will face cancer in our lifetime, and 50% of the cancer patients rely on radiotherapy at some point of their treatment, at least in the UK. But this amounts to just 5% of the government cancer budget, so it's a very highly cost-effective treatment. And I brought here 2 pictures, one from the past and another one from the present. And the picture from the past is from the Royal Marsden Hospital in London. And these patients are actually receiving a type of radiation treatment where they are holding with their hands a radioactive source close to the region that we want to treat. And what I found most intriguing is that you can actually picture a nurse lighting up a cigarette of a patient while receives treatment. Thankfully, things have improved from that, and nowadays we have radiotherapy machines that can target these radiation beams at a millimeter precision to the tumor. And of course, the success of the radiotherapy really depends on delivering the correct dose to the patient. And for that, we need accurate measurements. So in the 1900s, NPL measured radiation based on simple methods. And throughout the years, we developed new quantities that are more clinically relevant. And in 1988, NPL launches the first calibration service of absorbed radiation dose for high energy photons. And more recently, we've done the same for protons. So why radiation dose accuracy matters in this graph, we can see healthy tissue damage probability in function of radiation dose. And these curves are typically very steep and strongly dependent on the radiation dose. And a small variation on dose of the level of 5% can lead up to 30% more risk of damage. So it's very important to measure this quantity very accurately. That's why we develop our primary standards that can measure these quantities from first principles with appropriate uncertainty. And when new modalities come into place, we need to develop the standards to measure the dose of those new technologies as well. And an example of that is the case of protons. So for those who are not familiar, just made this quick schematic to show some of the benefits of the proton. So we have a radiation beam, and we can see the cross-section of a patient in pink, and in green, the region that we want to treat, our tumor. So high energy X-rays, they just go all the way through the body, and they deposit some dose in the tumor, but also in the healthy tissues. As opposed to high energy photons, protons, they have a mass, and because they have a mass, they will stop. And we can control the energy of the protons to stop exactly where the tumor is, and these allow us to have a much more conformable dose to the tumor in comparison with other modalities like high energy photons. So the code of practice for protons was developed with the aim to deliver an uncertainty on reference dosimetry for protons of the level of 2% at k=2. So this was really to bring uncertainty on protons to a similar level to what we already delivered for high energy photons in the UK. So for that, the code of practice is based on our NPL dedicated primary standard for proton. And the idea to achieve this uncertainty was to calibrate these beams, to use our calorimeter directly in the user beam, so going away from the cobalt-60 route. Because we do not have a beam at NPL, a proton beam at NPL, we had to develop our primary standard to be transportable. So the idea is to perform the calibrations at the clinical facility in the user beam. So for that, we had to make our detector robust. Our racks have suspension built into them to help protect instrumentation from vibration. And the whole system is operational within 2 hours of arrival. And this is very important because we are performing measurements in clinical facilities, and the priority there is to treat patients. So time is very limited. So we need to be very efficient and effective in the data that we collect. Okay, so the code of practice was published through IPEM. So for those who are not familiar, IPEM is the Institute of Physics and Engineering in Medicine, and it is the UK professional body for medical physicists. And IPEM publishes code of practice for the clinical community to follow to ensure accuracy, safety, and consistency. And you can see here the working group, and it is composed by a group of metrologists, but also a medical physicist. And we have a representative medical physicist for all the proton facilities that exist in the UK. So here are some of our reference conditions. The calibrations are performed in the spread out break peak, or what we term as a standard test volume. So we have a dose volume that is uniform. So for that, we require beforehand a treatment planning system that it is commissioned. I know this is a bit unusual in a code of practice, but it does mean that we correct the performance of the whole dosimetry chain, including the treatment planning system. And this is what actually the clinics care about, is the dose in the spread out break peaks. So we have 3 reference fields. So these are box fields of 10 by 10 by 10 centimeters cube homogeneous dose, and they are centered at different depths, and we've chosen these depths and these fields to make sure that we cover all the energy range that we use when we treat patients. And our dedicated chamber is a plane parallel roof, and this chamber was chosen due to its reproducibility and repeatability that we've been observed in this type of detectors throughout the years. So as a proof of principle of the code of practice, we performed validation measurements in different facilities, nationally and internationally, where we took our calorimeter to the clinics, to the proton beams, our primary standard, we calibrated a set of NPL transfer standards, our rules, and we also calibrate directly the user chambers. On the graph on the left, you can actually see a typical calorimeter run. So our primary standard is a calorimeter. So we measure the temperature increase due to radiation. And you can actually see the different energy layers being delivered in our calorimeter. And then on the right, we perform the comparison where we compare the dose from the IPEM code of practice and the TRS 398 route that bases calibrations in cobalt-60. There was the IPEM code of practice measures a dose that is consistently lower in comparison with the TRS 398, but nonetheless, both protocols agreed within their stated uncertainties. But just to refer that the code of practice developed at IPM gives a significant reduction in uncertainty in comparison with TRS 398. And, this is why we did it. So some main points of summary: the UK now has a set of codes of practice for photon, electrons, and proton beams, all based on graphite calorimetry. We did compare our proton calorimeter against our UK primary standard graphite calorimeter for photon beams at NPL, but would be very keen to also do an international comparison where we compare our proton beam with another standard in a proton beam. And the new procedure based on the calorimeter gives a significant improvement in uncertainty. So just a future outlook, as the number of cancer cases are rising, we need to meet this challenge, we can develop the measurement science to understand how different patients respond to radiation at the DNA level. We can also support the acceleration adoption of advanced treatments by developing the standards that make it safe and clinical usable, and also on AI by integrating safely into the clinic by providing the trusted and rigorous validation. And I think I'm just on time now, so thank you for listening. Merci beaucoup.
Okay, hello everyone. My name is Minju Lee from the radioactivity group at the CRIS, Korea. I am very happy to have this opportunity to share our research work. Today, I am pleased to present our recent work titled Development of SI-Traceable matrix-based activity CRMs for nuclear power plant decommissioning. Okay, in this presentation, I briefly introduce the motivation behind this work and the key steps in the development of these CRMs and how we aim to establish SI traceability through some international comparisons. Okay, now before I move on to the technical part, let me briefly introduce myself. I have been working as a researcher in the radioactivity group at CRIS since 2022. I have been conducting research on some production or some development of matrix CRMs and national reference standards. In addition to some certified low-level CRMs, I am developing some low-level gamma spectroscopies. Okay, let me briefly introduce CRIS. CRIS is located in Daejeon, Korea, and CRIS serves as the National Metrology Institute of Korea and responsible for establishing and maintaining and improving national measurement standards. We also conduct some research and development in science and technology, and also disseminate measurement standards to industry and many labs. Currently, CRIS has about 900 staff members, including around 400 research scientists and engineers. We also host visiting researchers and postdoctoral fellows from various institutes around the world. Okay, this is our group at CRIS. Our group is also responsible for establishing and disseminating activity measurement standard in Korea. Our team currently consists of 6 researchers and 4 engineers. We can now move on to the development of a matrix CRM by CRIS. Currently, Korea operates several nuclear power plants across the country, as shown on the left map. Among them, 2 reactors, the name is Curie Unit 1 and Wilson Unit 1, have been permanently shut down and are now preparing for decommissioning. So this is not only a domestic issue because worldwide more than 100 reactors have already been permanently shut down. So therefore, the safe and accurate management of decommissioning waste has become on some important global challenge. During the decommissioning process, large volume of waste are generated. So, for example, at the Yankee nuclear power plant in the United States, over 120,000 tons of decommissioning waste were produced, with concrete and soil accounting for the majority. Okay, among this waste, there are 14 key radionuclides that must be accurately identified and quantified, including some tritium and carbon-14 and cobalt-60, nickel-63 and strontium-90 and so forth. To ensure accurate the assessment of these radionuclides, we need some validation of the new measurement procedures and verification of the analytical results. Also, we, in particular, radionuclides that must be measured by alpha or beta techniques, some require radiochemical nuclide separations. So therefore, the chemical recovery or chemical yield must be determined to correct for losses during processing. For these reasons, Matrix CRM provided the necessary tools for validation, verification, and yield determinations. Okay, the main goal of our project is to develop a matrix-based activity CRMs with SI traceabilities. Our target matrix include concrete and soil and metal and another matrices related to the decommissioning waste. And the key radionuclides we are focusing on are the 14 radionuclides that must be identified in decommissioning waste. Okay, to establish SI traceability for the developed matrix CRM, we follow the established traceability chain from the primary standards down to the CRMs. First, we establish international equivalence for our primary standard through key comparisons. At CRIS, the now radioactivity CMC list currently include around 189 items. Next, we calibrate the certifying system, and such as the gamma spectrometry system or some liquid scintillation counters using secondary standards that are traceable to the primary standards. Finally, the matrix CRM is certified using the certifying system, ensuring the SI traceability of its some activity values. At CRIS, all activities related to reference material production and calibration service are managed under the some quality system. We operate under ISO 9001 and 97025 quality systems. We also accredited to 17034 standards as a reference material producers. Based on this framework, CRIS produces a wide range of CRMs. The crucial activity for production of the CRM were carried out in accordance with ISO standards. So we perform the homogeneity is evaluated using ANOVA testing. And also we perform stability testing using the linear regression analysis. After that, the property value are determined based on the some mean value of the measurement results. And finally, the CRM uncertainty is evaluated by combining the uncertainty component from between Bert variation and within Bert in homogeneity and type B uncertainty. Okay, to date, as shown in the table, we finally have developed 3 CRMs, concrete, soil, and liquid type metal CRMs. Following the stability testing, and we have a plan to register these CRMs with Chris.
Minju, I'm sorry, the 10 minutes are up. Could you go to your conclusion, please?
Yes. Okay, this is my last slide. Okay, the key point of my presentation is to develop SI-Traceable matrix CRMs for decommissioning waste, and we finally disseminated them internationally. So, okay, this is the end of my talk. Thank you for your kind attention. Thank you.
Good afternoon, everybody. It's a great pleasure for me to be here today. And I'd like especially to thank Vincent for giving me the opportunity to talk today. So I was given the daunting task of talking about nuclear data for radionuclide metrology, past, present, and future. I'm going to try to be on time, not to be scolded. Unfortunately, I hope the head of my lab will not be bothered too much. I don't have a slide introducing my laboratory. I'm from France, working at LNE-LNHB. Hopefully, will not hear about that. So, I thought that the starting point would be to define what are nuclear data. What are we talking about? From a very general point of view, I would say go back to the basic. What we're working with is a quantum system, a very complex system. Actually, it's a many-body problem. We have both a nucleus composed of proton and neutron bound by the nuclear force. We have also the surrounding cloud of electron bound by the electromagnetic force. And the question is, as a physicist, if you want to describe the system, if you want to observe it, what can you do? Well, there is 2 ways to do that. Either you are experimentalist like myself, and you will try to do something, measure mass, measure, for example, a cross-section, you launch your nuclei onto something in a way to see something. Or if it's a radionuclide, as what we are interested in, we will look for half-life, emission of particles, and stuff like that. That's the first option. The second option is that if you're a theorist, you will solve a very complex equation that I've written there, even though I'm not sure how to solve that. But you will be also able to get information. Keep in mind that this information will be different. You will access what they call the wave function, so we'll get information such as size, the shape, deformation sometimes, spin parities and stuff like that. Why am I talking about that is that because if we want to talk about nuclear data, it's both experimental and theoretical information. Nuclear data are all the information we can get on these nuclei, whether they are calculated or observed directly. And that's important because obviously, depending on your need, you will call either for one or the others. And quickly come the question is, how do you know what you're doing when you have to be both knowledgeable about theoretical calculation and experimental data? Also, in experiments, if we take an example of half-life, you can have measurement about state that takes picosecond to decay, or nuclei that take up to more than the age of the universe to decay. How do you deal with that as an experimentalist? You cannot be expert of everything, and that's a bit the problem with nuclear data is high expertise is required. So you are knowledgeable enough to choose the data you're taking for your application. The idea of recommended data, and nuclear data in general, is to recommend data for people so they don't have to think about it. There's a hint there They don't have to think, and that's sometimes a problem. But anyway, so what about radionuclide metrology? Well, at some point, one way or another, primary and secondary activity measurements rely on nuclear data. It can be the decay scheme, it can be the intensity, but one way or another, we rely on this nuclear data. And that's actually something important. Back in the 90s, people were doing as they wish, let's say, and doing intercomparison, they started to see discrepancy. They end up seeing that the different labs were not using the same data. Obviously, if you don't use the same data, whatever is your measurement, you're not going to end with the same answer. Hence was launched this idea of having an international group called the DDEP that was founded in 1995 that answer this need to have a common set of nuclear data. Actually, on a note, we were discussing, and Vincent very nicely told us about the 150 years about the BIPM. I'm a bit sad that it overshadowed the very important 30 years of the DDEP, which is something that I'm sure Mark wants me to highlight. But nevertheless, the group was founded, and the idea was, thanks to the BIPM that bringing support through the CCRI, by recommending DDEP as data to be used in radionuclide metrology intercomparison. So what is this about? The idea is to have an international effort about a group of experts from all the lab. So we had many labs over the years, LNHB, NIST, IFIN, PTB, NPL, many labs, even CAF from China. So all over the world, people working together with a common set of rules in order to recommend data for the users. These data, they are easy to use, comprehensive, and really dedicated to non-specialists. And that's very important. We provide all that is needed in principle for radionuclide measurements. So half-life, Q-value, decay scheme, intensity, and energies. Okay, so what's the current status? Currently, the DDEP is coordinated at LNHB by Xavier Mouchot. We have about a dozen of core members, and over the 30 years of its existence, we end up having up to 232 evaluations of different radionuclei, which is quite an impressive numbers because it covers most of the need of the people in radionuclide metrology. Actually, these evaluations were performed according to needs because we're working for our users, which are mainly metrologists. DDP quickly become important to the point that we get a reputation and we started to work in collaboration with other institutes. And I think we have to highlight the CRP with the IAEA that have been done over the years and that have been extremely helpful to produce a high number of evaluations. But we're also working with Jeff Library, the CTBTO, and so on and so forth. So our data, the goal of this data is to be usable by anyone. So we disseminate them freely and openly to anyone, first through our website, but also through what is called an online tool called LaraWeb. With the help of the BIPM, we're also publishing them in the so-called BIPM monographies. 8 volumes have been produced, and also we have a small table that we're producing with that. So that's the current status of the DDEP. We are trying to improve that, to work on that, and to move forward. So what is the short future of DDEP? The future is a new version of the mini table that hopefully we will publish next year. But also, what we are doing is changing our approach. For long last, we have published in the monography of the BIPM, and thanks with a discussion with our colleague from the BIPM, now we will publish our results and evaluation in Metrology, which is much better for everybody because we can easily refer to a DOI, which is a much easier things to do nowadays. Last but not least, we are also updated our online tool very regularly. Lately, our colleague Christophe Dulieu, who is in charge of that and that should get all the credits, has been working on a decay chain tool. So you can input a decay chain and calculate the intensity of all the elements at some point in the decay chain, given an amount of time. Lastly, we're also working on putting new tools online. Here's an example of the beta shape code where we can have online display. So I was told that I'm in the young metrology part. So as a young person, I'm quite subversive, and I will come to this question. I hope that's the hope, that's the goal of having young people there. Well, if we have 233 evaluation covering most of the radionuclei, well, is it still useful to perform evaluation? Is there any sense of that? So I was hoping to have to make a shock, but unfortunately, my previous speakers, especially Hao-Han, has done a wonderful job explaining why we need evaluation. So the short answer is yes, we do need evaluation. Why is that? Well, the first thing is evaluation is a never-ending progress. As soon as we have new data, we can update what we have done as evaluator to go to a refinement of our evaluation. Second thing is that even though most people believe that nuclei are well known, the reality is unfortunately not as good. I will go to shortly. And an example is cesium-137, which is proven here, which is one of the most widespread nuclei, but the intensity measurement of the main gamma ray is not well known. So the second thing is, and it has been said many times, is that we need new evaluation for new isotopes in medical application. So the important thing, and I will stop there, is training tomorrow experts. I've been pleased to hear through Vincent that the BIPM is interested in furthering its link with nuclear data, and that's something very important. So we're very looking forward collaborating more closely with the BIPM, and I've also been very happy to see my previous speaker speaking about that. So what we're doing is organizing workshop to train people, not necessarily to become evaluated, but at least to know how to use this data. So we are doing that every 2 years. We're also collaborating closely with China on that. So my takeaway message is, are you ready to embark on the journey of nuclear data? Thank you for your attention.
Okay, so hi everyone, good afternoon. First of all, thanks to the organizer for giving me the chance to deliver this short talk. I will be brief. So I come from the CCRI in Mexico. We are the Center for Ionizing Radiation Metrology in our country. So here in Mexico, the NMI is the CINAM. CINAM is the institute which holds most of the standards in all of the magnitudes. All of the magnitudes, but the ionizing radiation magnitudes, we are the designated institute for those magnitudes. So we are ININ, the National Institute for Nuclear Research. You can see here a picture of our institute. Everybody's welcome to visit. It's a very nice place. It's a very nice place to be. And well, this institute it's large and it has a lot of research lines and research groups in every field you can imagine. One of them, it's the ionizing radiation metrology, which is only a department in this institute. This is a picture of our department. We're behind the mountain, so we're kind of far from the rest of the institute. So our institute is formed by 3 groups following the same structure the CCRI follows. We have the Radioactivity Standards Lab. They have 45 CMCs published at the KCDB in activity and efficiency for gamma emitters, alpha, beta, and gamma emitters. Most of the capabilities of this group are gamma spectrometry based. And then we have the secondary standards dosimetry laboratory. They have 15 CMCs. 5 of them have been recently published, actually by a young researcher also. Ángeles Montes, maybe some of you have heard of her. I've seen her work and I'm trying to follow because I'm trying to develop the capabilities for the neutrons area, which is the main topic of this presentation. So what we have now in the neutrons field is we have this room. We have a calibrated americium beryllium source. It's calibrated both in emission rate and anisotropy. We have the calibrated graduated metal ruler and an automatic pneumatic positioning system, which you can see here. This is the system we use to place the source in the same place every time and in a safe manner for, you know, the protection of the workers there. We usually use nuclear electronics to get the signals from the detectors we calibrate. We have the, you know, the preamplifier and the amplifier and the multi-channel analyzer, so we can extract the data from the detector, and then we calculate the response of the detectors, and then we can actually calibrate in the radiological protection magnitudes. Our room has an octagonal geometry. You can see here a diagram. It has 4 walls, which are made of concrete. This is for radiological protection because this is a common area. And then you have the remaining 4 walls are carbon steel thin sheets. The blue ones you can see here. Now this is a control area, so nobody's here. So this is our calibration line. You can see the symmetry in the room. The room has a false floor under which there is a 3-meter tall basement. Down here we have the shielding for the source, and the calibration line is up here. It's 5.6 meters above ground to reduce the scattering from the ground. You can see also here there is a false ceiling, so we don't have those neutrons coming back from the top of the roof. Now we are 3 people involved in the neutrons calibration room. This one here, the one next to me, he's a student. He just got his physicist degree yesterday by working with us, doing this evaluation of the scattering of the neutrons with a scintillator in a moderating sphere. The remaining 3, we are working at the neutrons room. We have been trained thanks to IAEA and BIPM. We have been at the IRD in Brazil. They were very kind and very nice and very helpful. That was in 2023. In the past month, I've been to NIST also. This was sponsored by SIM. They were also very kind and very useful and very nice. So we have been at NIST also, and we have been learning from the INM in Colombia, and we are actually always getting feedback from CINAM. They know all of the metrology stuff. At the time, we calibrate close to 100 personal and area dosimeters per year. This is in an americium beryllium reference field. We use a semi-empirical method to determine the contribution of the scattered neutrons. We have validated this method against the cone method, the shadow cone. You can see here, actually, this is a picture of Bruno. Bruno is the student I told you about before. This is one of the pictures he has in his thesis. And also he has this publication in the web, in an EPJ web conference. And so with this shadow cone technique, we validated the semi-empirical method we use for every instrument we calibrate. We have validated this method for this detector. This is a scintillator, and for personal dosimeters in the Phantom. We are implementing the Bonner spectrometry, so we can also validate the use of our fluence to dose conversion coefficients. At the moment, we are just increasing the uncertainty on these conversion coefficients. So we want to decrease this uncertainty by measuring the actual spectrum of our field. And we are also implementing Monte Carlo simulations. We are trying to validate the OpenMC results we are getting against our measurements. So we can also implement simulation results into our services and the future developments. Now, in our short-term plans, the most important task I've been assigned to is to align our neutron processes with the CMRI quality management system, which has been approved by the QSTF of SIM. This has been approved in 2023, and we want to increase the scope to the neutron capabilities in the next 2028. So this is what we're working on right now. And then we also want to acquire a Californium-252 neutron source to establish a Bert and a moderated Californium field, also basically for personal dosimetry services. We have in Mexico 2 nuclear reactors, so it's a necessity to establish these reference fields. And actually, when I was at NIST, that was the main goal of my stay there, to see how to implement these new reference fields in Mexico.
I'm sorry, Marisa, the 10 minutes are finished. If you could go to your last slide.
Okay. Next, we want to put a manganese sulfate, but this is a further away plan. So this is what we're working on. Thank you so much for your attention.
Thank you and good afternoon, everyone. It's an honor to participate in this workshop today. My name is Khalid Mustafa, Assistant Researcher at Ionizing Radiation Metrology Laboratory, National Institute of Standard in Egypt. The topic I am going to present is towards primary standardization on neutron dosimetry, especially calibration of neutron sources using the manganese bus technique. Our Ionizing Radiation Metrology Lab is a secondary standard dosimeter laboratory at National Institute of Standard in Egypt. Its goal to achieve a complete traceability for different ionizing radiation metrology fields. From its activity, a neutron dosimetry, the laboratory develops its capability to transition from the secondary standard level to the primary standard level by constructing the manganese bus system. The manganese bus system is a primary standard method using for determining the neutron emission rate of different neutron sources. This system was used since 1960 until now. The main concept of this technique is irradiate manganese solution inside a sphere container after immersing a neutron source inside the center of the bus. The first neutron thermalized after elastically scattered with hydrogen atom. The thermal neutron then captured by the manganese atom that converted into manganese 56, which beta decay with emission of gamma ray. The activity of gamma ray measured after 24 hours by one of 2 techniques, sodium iodide detector or coincidence system. The emission rate calculate from the equation B equal A divided into some correction factor A obtained from the experimental data extracted from a coincidence or spectroscopy, and the correction factor calculated from the Monte Carlo simulation. From the literature view, the most sources were used are californium and americium beryllium for different activity. According to the literature review, the bus geometry is aspherical and is made from stainless steel or plexiglass material. As shown in figure, we have two spheres, plexiglass and stainless steel. The diameter of stainless steel, according to literature review, varying from 34 to 125 centimeters. For enhancing manganese bus accuracy, we have two stages. The first stage, detector system calibration. We calibrate the detectors by two methods. The first method using standard reference Maranelli, and the second method is irradiate manganese solution to a steady flux by reactor. The second way is Monte Carlo modeling. This Monte Carlo using to calculate a different correction factor that cannot be determined experimentally. Monte Carlo can be used in different codes such as MCNB, Fellag, and scale. There are a number of different interlaboratory comparisons are carried out by using manganese bus system. For comparing a neutron emission rate measurement between a primary national metrology laboratory. The first comparison at interval between 1999 to 2005 between 8 laboratories, and they used the same americium beryllium neutron source. The calculated degree of equivalence for each laboratory revealed both satisfactory and unsatisfactory performance. And the figure shows how each lab results is distributed around the assigned value. The second interlaboratory comparison at 2016 between 10 labs, and they used the same californium neutron source. The degree of equivalence was calculated for each lab and indicated that all labs have satisfactory performance. And also the figures show the distribution for each lab around the assigned value. Now, the literature review was the first step towards a primary standard system. The next step for ionizing radiation metrology lab began in 2018 with the construction of a prototype manganese bus system for measuring a low activity neutron source. Our manganese bus consists of 3 parts. The first part is a sphere with diameter 34 centimeters and thickness 5 millimeters. The second part is hydraulic system, consists of pump and filter. The third part is a detection system, consists of a spectroscopy system with sodium iodide detector, and Maranelli has the same geometry of the standard reference one. As we mentioned before, for enhancing the manganese bus accuracy, we calibrated the detector by using reference standard Maranelli. The low activity californium is a neutron source was used with a certified value 178. We prepared 3 different molarities for manganese sulfate solution, and we obtained the different fluxes with enhanced uncertainty by increasing molarity. And we noted that the 2 molarity of 1.18 and 1.48 are agreement with the certified value as shown on figure on the right. We published a paper entitled by Prototype Manganese Solution Bus for Low Activity Primary Standard Neutron Dosimetry at Radioanalytical and Nuclear Chemistry, discuss this subject. After that, we design and construct ionizing radiation manganese bus to determine the emission rate for different activity for different neutron sources. Our manganese bus has consists of 3 types. Consists of 3 parts. The first part, sphere with diameter 100 centimeters and thickness 5 millimeters. The second part, hydraulic system, consists of 2 flow meter, filter, and pump to circulate solution from the bus to the other part of the system. The final part is the detection system, consists of spectroscopy system with sodium iodide detector, and the standard Maranelli from stainless steel 1 liter has the same geometry for the standard reference 1. Also, as mentioned before, for enhancing manganese pass accuracy, we calibrate our detector system by using a reference standard Maranelli, and also we using Monte Carlo simulation to calculate correction factor. We using in this experiment americium beryllium 1 Curie as a source was used with a certified value 2.22 e⁻⁶ neutron per second. Before using the Monte Carlo codes, it was necessary to validate the code. There were several ways to validate the code. The first one, neutron equivalent dose. The figure on the left shows the agreement between the calculated and the measured value of the neutron equivalent dose at various distance in air for americium beryllium 5 Curie. The second way is neutron energy distribution inside the bus, as shown in the right figure. The neutron energy was thermalized after traveling a distance through the manganese solution inside the bus. The third way to assure the validation is validate the correction factor and the emission rate. Table shows agreement between the value obtained from the IRML Monte Carlo simulation and the reference value provided by the various national metrology institute. After we make sure from the validation of the code, we calculate the leakage for gamma and the neutron doses for different ratios from hydrogen to manganese atom. We noted that there is a small leakage, and we take it into account in our calculations. We published a paper entitled by Monte Carlo simulation of neutron interaction in manganese bus used for primary standard neutron dosimetry in nuclear engineering and technology. After we simulate the system, we prepared different polarity for manganese sulfate solution to obtain the optimum condition that verified the certified emission rate through post-experimental and Monte Carlo simulation. And finally, we calculate the uncertainty budget from different sources of error. We now preparing a manuscript for publication. Sorry. The ionizing radiation future work is to participate in interlaboratory comparison with the primary National Metrology Institute to determine the degree of equivalence. Thank you.
Hello, everyone. My name is Haya Al-Arifi. I'm health physics technician from King Faisal Special Hospital and Research Center. Today, I will present an overview for our neutron calibration metrology and ongoing project. In the first, I will talk about our SSDL in the Research Center. Is established in 1980 and they become a member of the SSDL network since 1988. Also licensed by the National Radiation Regulatory Authority in Saudi Arabia, NRC. Also, we provide calibration services and irradiation services for radiation protection, gamma, X-ray, contamination, and neutron. Also, diagnostic radiology, radiotherapy, including the brachy. For now, we're serving more than 400 customers. Also, we do more than 2,000 instruments overall per year. Here we can see before and after 2022. Before we use an LINAC as a neutron generator and we issue verification certificates. After 2022, we established a new facility of neutron calibration using americium beryllium. And as see here, for 2025, we show the data just for 30 quarter, so there's still more. After that, we see here a neutron facility overview. First of all, our reference is americium beryllium source with the 3 Curie. And this is the facility dimension. And we do a simulation to evaluating the scattering effect in instrument reading. And we see it's under 150 centimeter is less than 40%. So we indicate some distance to do the calibration, which is 15, 16, and 140, 70 centimeter, which with accepted limit. After that, we see here the metrology and the calibration. We use the method of transfer instrument, compare the client instrument with our transfer instrument in the identical irradiation conditions with the substitutional method. After that, we see here our reference transfer instrument, Berthold, which was calibrated and NRC Canada. After that, we can see our project Shadow Cone. We have homemade 10 stainless steel boron doped polyethylene cones with different diameters and also with the different concentrations, so we can study the evaluation scattering neutron with different neutron detector size. Also to study the effect of percentage of doping boron to the reading. Also, we ongoing to custom holder to ensure the stability, accuracy, and reproducibility for the reading. And we have also done a proficiency test in neutron calibration in 2022-25 with NIST and Fanner. The result shows very good argument with the reference lab, confirming our measurements accuracy and traceability. Also, this will support our quality assurance and compliance with ISO 17025. Finally, our future directions to determine scattering components using shadow cones and analytic methods. Also perform spectrometry of neutron facility using Polar spheres. Also strengthen the capabilities of calibration. Also expand the research in neutron metrology, and finally developing skilled metrology workforce. And thank you so much for your attention.